Hello and herzlich willkommen bij Nocturni, docs wo sich dein Nugierde sam fam rande de Nacht nicht und die Wissenschaft sich langsam und geduldig ausbreitet, bis das Unbekannte dein Stück näher scheint. Heute Abend begeben wir uns an einen Ort, den kaum ein Mensch betreten hat. Heute Abend begeben wir uns an einen Ort, den kaum in einen nicht, weil wir nicht wollen, sondern weil die Erde selbst uns Widerstand leisten scheint. Wir eisen zum Nordpol, jenseits von Schnee und Still, vorbei an dem kaltesten Winden und hellsten Eis. Zu einem Ort, der lange verschlossen war, als die Menschheit existiert. Unter den Gletschern des Nordpols liegt eine verborgene Welt enormer fremdartig und fast völlig unerreichbar, und trotz unserer Technologie, all unseres Ehrgeizes und all unseres Ehrgeizes und all unserer Termengsen forschen können wir nicht mehr. Doch bevor wir wohl in die Tiefe tauschen, möchte ich gern wissen, woher hören Sie und heute Abend zu? Und wie warm ist es bei Ihnen? Wie leicht ist es warm? Wie leicht ist kalt? Aber ich kann Ihnen versichern, das ist bei weitem nicht so kalt, ist wie an dem. Wir bestücken, während wir gestoßen werden. Wenn Ihnen diese Art von stille Neugierde so sagt, würde ich mich sehr freuen, wenn Sie dieses Video liken oder meinen Kanal abonnieren würden. Nocturni Druck hilft diese kleinen, beschaulichen Ecke der Wissenschaft, mehr Menschen zu erreichen, die weiterhin bemannt durchgewinnen. Machen Sie es sich becken, beruhigen Sie Ihre Gedanken und folgen Sie mir nach Norden. Denn die Geschichte, die wir heute Abend erzählen, war Millionen von Jahren unter dem Erwachen. Der Nordpol ist eine seltsame Art von Grenzgebiet. Er ist kein Berg, den man bestigen kann, kein Ozean, den man befallen kann. Er ist ein Ort, der nicht so sehr vor uns steht, sehr vor uns schwebt, verborgen unter Hunderten, manchmal Tausenden von Meternischen. Wenn wir an den Nordpol denken, stellen wir uns oft eine endlos weiße Fläche vor, die sich bis zum Horizont erstreckt, eine konturlose Ebene, die nur gelegentlich von einem Wellen oder einem urgentlich Fläche unterbrochen wird. Aber das ist nur die Oberfläche. Unter dieser gefrorenen Wüste liegt eine Landschaft, die wir kaum verstehen. Flüsse, die fließen, ohne jemals die Luft zu berühren. Seen, die lange von der Sonne abgeschnitten sind. Allanza von der schicknichten Gen, allanza speziesisiert. Und vielleicht sogar Ökosysteme, die sich in bulliger Isolation entwickelt haben, vom Rest des Planeten durch eine Barriere ausdrückendem, sie zwischen einem gefrorenem Gewicht gestanden. Es ist nicht nur so, dass wir die Arktis nur ständig erforscht haben. Es ist vielmehr so, dass wir es bisher nicht können. Die Arktis wie das ist sich nicht nur dem Eindringen, sie vernichtet unsere Versuche. Maschinen, was wir sagen, Maschinen, welche gehen, Sensoren fallen aus. Es schließt sich dem alles, was wir in seine Tiefen hinablassen wollen. Je tiefer wir vordringen, desto stärker scheint die Umgebung Widerstand zu leisten. Und doch ist es genau das, was dieses Mysterium so unwiderstehlich machte, denn irgendwo unter all dem Eis wird beherrschte schöne Welt, wie teils Erde, teils fremder Planet ist, und wir wollen unbedingt wissen, was sie birgt. Zu verstehen, warum sie so schwergänglich ist, müssen wir zunächst verstehen, was wir überhaupt erreichen wollen. Götter sind nicht ein vergörenes Wasser, das an einem Ort tuchen ist. Wasser an einem Ort. Sie sind dynamische, lebendige Systeme aus Räume, die sich unter ihrem immensen Gewicht bewegen und verschieben, Die Gletscher rund um den Nordpol gehören zu den ältesten und mächtigsten der Erde. Einige sind über 2 Meilen im Jahr alt und wurden durch unzählige Frosthörtenseichen geschichtet und verdichtet. Stellen Sie sich nie vor, Decke der verschachhunderte fürchende Filt, nie vollständig schmilzt die darunterliegenden Schichten so lange durchgehenden Schichten so lange drückt, bis sie so festem Eis verschmelzen. Per Jahrtausende wird dieses Eis dicker, tiefer und beginnt unter seinem eigenen, kolossalen Gewicht nach außen zu fließen. Das ist ein Gletscher, ein langsamer und aufhaltsamer Eisstrom, der sich seinen Weg durch die Landbahn zur Erde, der unter sich formt. Und die Ströme sind nicht nur die, sie sind gewaltig. Das Eis, das den arktischen Ozean und den nahegelegenen grönländischen Eisgebiet deckt, kann Tiefen von über 3 Kilometer erreichen. Das ist, als würde man 3 Eiffeltürme beieinander und die würden plötzlich die Mächte durchbrechen. Es handelt sich nicht um einen zugefrorenen Teich. Es ist ein gefrorener Kontinent, der mit unvorstellbarer Kraft drückt. Stellen Sie sich nun vor, was unter dieser ist massig. Das Gewicht ist so immens. Das ist die Landschaft darunter sehr malm und die fatale, subglaziale Becken und werbegene Kanäle, formiert durch Schmelzwasser fließen kann. An manchen Stellen äußert der Druck von oben so viel Hitze, dass die unterste Eisschicht schmilzt, obwohl die Temperatur weit wohl die Temperatur weit unter dem Gefrierpunkt liegt. Dieses Schmelzwasser bildet Fluss und zieht unter dem Gletscher, abgeschnitten von der Außenwelt. Da sind nicht die Art von Ziehen, die man mit dem Butiberg hören würde. Sie sind stockdunkel. Sauerstoffarm und durch kilometerdiches Eis vom Sonnenlicht abgeschnitten. Und doch schönten einige von ihnen seit und dahin von Jahren und gestortet sich den. Wissenschaftler wissen das, weil wir ähnliche Umgebungen in der Antarktis untersucht haben, wie den See, ein riesiges Gewässer, das unter 4 Kilometer ist begraben liegt und seit etwa 15 Millionen Jahren Jahren unberührt ist. Die Arktis birgt mit ziemlich hoher Sicherheit antike Wasser, die uns jedoch verborgen bleiben. Radar kann ihre Existenz andeuten. Satellitenmechanen können selbst kleinste Ausbuchtungen und Strömungen im darüber liegenden Eis erfassen. Aber so wirklich erforschen, so zu sehen, Proben zu entnehmen und zu scheren, mich schon wichtig verstehen, müssten wir dorthin gelangen. Und genau da beginnen die Probleme. Durch kilometerlanges sich bewegendes Eis zu bohren, ist nicht nur schwierig, sondern eine der größten technischen Herausforderungen, denen sich die Menschheit gestellt hat. Es ist nicht Einheit, sondern geschichtet. Von blassen Durchstocken, rissig und je tiefer man bohrt, desto höher wird der Druck und desto saftflüssiger verhält sich das Eis und fließt langsam alle Sicherheit, was man hineinzuführen versucht. Erhöht die Bohranlagen, wie sie so edel lollet oder goldene Förster eingesetzt dürfte, sind dafür nicht sie gut. Sie benötigen festen Untergrund, nicht einen sich ständig verformenden Eisblock. Selbst Basili, Thermobucherer, die sich durch Schmelzen nach unten vorarbeiten, stehen vor enormen Herausforderungen. Während wir absinken, kann das Eis hinter ihnen wieder fliehen und den Schacht verschließen. Je tiefer sie bohren, desto schwieriger wird es, ein stabiles Spor zu erhalten. Und selbst wenn man den Grund erreicht hat, wartet eine weitere Herausforderung, Contamination. Die Ökosysteme unter dem Eis, sofern sie existieren, sind seit Hunderttausenden oder sogar Millionen von Jahren isoliert. Die in ein einziges Sperrmodell Bakterien, die durch einen Becher eingebracht wird, kann die Proben durchsuchen. Daher müssen Wissenschaftler ihre Komponente, jeden Tropfen Flüssigkeit und jede Strinte ins das Eis eindringt, Startensismente. Sterilisieren. Es ist in langsame, tue unglaublich heikel Arbeit. Unter arktischen Bedingungen können wir schwerer. Die arktische Umgebung selbst bringt zusätzliche Komplexität mit sich. Anders als in der Antarktis, wo ein Großteil des Eises auf dem Festland liegt, ist der Nordpol von Meer jetzt bedeckt, das ab dem Ozean treibt. Die Eisis ist nicht verankert. Er ist weit, behasst und verschärft, sich ständig unter dem Einfluss von Wind und Strömungen. Eine Bohrplattform, die an einem Tag perfekt positioniert ist, kann am nächsten Tag kilometerweit vom Seil abgetrieben sein. In Eis verankerte Ausrüstung kann durch Eisbruchstücken, massive aus verborgenem Eis, die sich ohne Verwarnung bilden, auseinandergerissen werden, ist heute Niveau dünn. Schon die Logistik des Betriebs in einer so abgelegenen und wörtlichen jungen und wörtlichen Lumbuken ist gewaltig. Die Temperatur der GCC. Winde können Geschwindigkeiten von über 100 Kilometer erreichen, und die Pollenach kann Monoplan andauern. Wird die Sonnenstrahlung unterbrochen und die Region in wohliger Dunkelheit gehuscht steht, das ist Rüstungsstil motiviert, dass diesen extremen Dämmungen standhält. Die Mission muss darauf ausgelegt sein, und jeder Fehler kann katastrophal sein. Mancher mag sich fragen, warum wir nicht einfach ein U-Boot unter das Eis sticken und von unten erforschen können. Schließlich sind Atom-U-Boote schon oft einer der Eiskappen durchgehandelt, das stimmt, aber sie sind noch nicht unter die Gletscher selbst vorgedrungen. Der Grund ist einfach. U-Boote sind für offene Gewässer gebaut, nicht für die Navigation im chaotischen Navigant und die Gletscherschelfen. Unter einem Gletscher ist die Grenzfläche ist die Grenzfläche zu der Eis und regelmäßig und fältig entfernte. Höllen bilden sich und sterben wieder ein. Kanäle winden sich unvorhersehbar. Es erstreckt sich in sehr klüfteten Graten, sogenannten Kais, nah unten von denen einige hunderte von Metern Oberfläche reichen. Selbst die modernsten U-Boote können es sich nicht leisten, ohne detaillierte Karten in solchem Gelände zu navigieren. Und diese Karten es nun navigieren. Und diese Karten existieren nicht, weil wir nicht dorthin vordringen konnten. Es ist perfektes. Paradoxon. Wir können die Welt unter dem Eis nicht kartieren, weil wir nicht dorthin gelangen können. Wir können nicht dorthin gelangen, weil wir es nicht kartiert haben. Robotersonden scheinen eine Lösung zu sein. Und in gewisser Weise sind sie es auch. Wissenschaftler entwickeln autonom Unterwasserfahrzeug-AUVs, die unter Eis navigieren, den Meeresboden kartieren und Daten sammeln können. Diese Roboter können Orte erreichen und ihre weiter wird Menschen unzugänglich sind, durch ingepassigen Leiten unter Direktsteuerung operieren. Doch auch sie stoßen an erhebliche Grenzen. Die Kommunikation durch dickes Eis ist nahezu unmöglich. Radar sollen dringen nur schlecht ein, und akustische Signale schwächen sich speichern sich schneller. Das Bett utert, sobald den Roboter und das es gelangt, ist erweitend auf Signale gestellt. Wenn es stecken bleibt, beschädigt wird oder verloren geht, können wenig tun. Die Akkulaufzeit ist eine weitere große Einschränkung. Der Betrieb wie eisigen Temperaturen die eine Kitzkeit in der glatte Innegeschenks. Dies ist keine Möglichkeit, tief unter dem Eis aufzufahren. Die meisten aktuellen AUVs können nur wenige Tage oder Wochen operieren, bevor sie auftauchen müssen. Das Auftauschen ist keine Option, wenn man unter einem Gletscher gefangen ist. Hinzu kommt der Druck. Je tiefer man unter das Eis vordringt, dass die Vermannung des das is vordringt, dass der Druck messer ist der Druckberie. In mehreren Kilometern Tiefe erreicht der Druck Hunderte von Atmosphären, genug, die meisten Materialien zu zerquetschen, wenn es sie nicht mit höchster Precision gefertigt sind. Das Eis setzt substitutbarsichtliche hönische Belastungen aus. Beim Fieten reibt es an der intelligenten Gestein und er sollte Reibung und Schäfte die Ausrüstung zerstören können. Schmelzwasserkanäle öffnen und schließen sich unwohlschätzbar. Mal werden sie vom plötzlichen Wassermaß nicht beflutet, mal frieren sie von ständig gestiegenen Massen beflutet, mal frieren sie wohlständig grachendig. Selbst die sorgfältigsten Sonden können ihnen durch Kräfte, die wir noch nicht vollständig verstehen, blockiert oder zerstört werden. Dies ist mit ein Grund dafür, dass die Erforschung der arktischen Gletscher so langsam voranschreitet. Jeder Versuch lehrt uns mehr darüber, was wir nicht wissen und wie wir nicht, auf die Bedingungen vorbereitet sind, die uns erwarten. Es ist verlockend, die Arktis als statisch, als gefrorene und veränderliche Ozeane zu betrachten, doch das ist eins der größten Missverständnisse. Die Gletscher sind ständig in Bewegung und fließen von ihren Entstehungszentren in Richtung Meer. Diese Bewegung lässt sich in Metern messen, doch aber Jahrzehnte oder Jahrhunderte formt die gesamte Landschaft und formt die gesamte Leben es. Hellen stürzen ein, sie wandern, Kanäle werden verschlachtend neu entstehen. Selbst die Dicke des Eises verändert sich, wenn Schnee sich ansammelt, schmilzt die, wieder gefroren und werdet. Wieder gefriert und werdet. Sehr bedeutet das Ziel, das sie ansteuern, möglicherweise gar nicht mehr existiert. Wenn es sie erreichen, ein Ziel erreichen. Ein subglasialer Ziel, der heute per Erde erfasst wird kurz, könnte bis zum Eintreffen einer Bohrung Jahr später durch den wirbelnden Horgenkanal enthoch, erzählt am Morgenkanal, entheike sich sin dürfte. Ein stabiles Schelfeis könnte nach einer Erwärmungsperiode von Wissen und Spalten durchzogen sein. Die Arktis ist kein gefrorenes Graf. Sie ist ein lebendiges, dynamisches System und das macht sie zu einem ständig verändernden Rätsel. Der Klimawandel verschärft die eisenschreitenden Rätsel. Die Arktis erwärmt sich fast viermal so schnell wie der globale Durchschnitt. Das Meereis wird dünner und zieht sich höher. Die Gletscher schmelzen in beispiellosem Tempo. Und da empfindliche Gletscher beschmelzen in beispiellosem Tempo. Und das empfindliche Gleichgewicht von Trüfte dem Eisverschgebet sich. Einerseits macht es einige Gebiete zugänglicher. Dünneres Eis kann leichter durchgedrungen werden. Und neue Kanäle connecten es ermöglichen, mit dem Wasser weiter vorzudringen. Andererseits werden die Bedingungen durch barrierischen Schilfe, die instabile Forschungsplattformen betennen, brechen und stürzen ein. Schmelzwasser kann auf unerhörte Weise wieder gefrieren, Bösen abschneiden und Geräte einzelleisten. Und die Ökosysteme, die wir erforschen wollen, könnten verschwinden, bevor wir sie überhaupt erreichen, verändert oder zerstört durch die heutigen Veränderungen darüber. Trotz dieser Hindernisse bleiben die Wandertürme, trotz dieser Hindernisse bleiben die Beine bis entschlossen. Die Arktis bietet Hinweise auf einige der größten wissenschaftlichen Fragen über Leben, Klima und sogar andere. Welten territoriale Umgebungen könnten mikrobielle Lebensformen beherbergen, die an Bedingungen angepasst ist, die wir einst für unbewohnbar hielten. Diese Erforschung könnte aufzeigen, wir leben in extremen Umgebungen erlebt und Hinweise darauf liefern, wie es auf eisigen Monden wie Europa oder Enceladus existieren kann. Die Sedimente Unter, es entfalten auf Zeitschlungen vergangener Klimate, angeschlossen in ungesteten Schichten, die Hunderttausende von Jahren zurückreichen. Die Entschlüsselung dieser Aufzeichnungen könnte uns helfen zu verstehen, wie sich das Erdklima verändert hat und wie es sich in Zukunft verhandelt hat und wie es sich in Zukunft verhandelte. Die physikalischen Prozesse unter den Gletschern können uns Aufschluss über die Eisdynamik, die Meeresspiegelanstieg und die Zukunft unserer Polarregionen in einer sich eröffnenden Welt geben. Dies Geheimnisse zu lüften, müssen wir jüdisch ein Problem lösen, das uns seit jetzt haftigt. Wie gelingt es uns, sicher, sauber und effektiv unter den eisigen Schutzschild der Arktis zu gelangen? Es gibt vieles prägend an sich. Einige Forscher entwickeln Roboter-Sonden, die sich mit Hilfe der warmen nuklearen Energie kühlen durch das Eis schmelzen sollen. Diese Geräte könnten theoretisch kilometerdickes, Jahrhundert und teredickes Eis durchdringen und Instrumente zur Untersuchung von Wasser und Sedimenten darunter transportieren. Und der Experimentier mit Laborhunden, bei denen fokussierte Energiestrahlen schmale Schachte durchächte das Eis hineiden, ohne die kontaminationsherrlicher hermlicher Methoden, wieder an der schlagen Hybrid-System vor. Die Bohren mit autonomer Navigation kombinieren und schwere kleine Sonden einsetzen, die zusammenarbeiten, die Unterwasserwelt zu kartieren und zu bewachen. Sieht der Seher. Idan steht vor enormen technischen und logistischen Herausforderungen, doch sie sees Juden von einem waschenden Willen, den Schleier unter dem Nordpol rufen. Ob einer der Seher Idan erfolgaten wird, bleibt abzuwarten. Die Arktis unter dem Eis bleibt welches eines der letzten großen Rastel der Erde. Wir wissen, dass sie existiert, können sie aber noch nicht erreichen. Ein Fiebertennisjager, Dunkelheit und Zeit da. Dunkelheit und Zeit. Jeder Versuch, hier zu erforschen, lehrt uns Neues über unser Planet und über die Grenzen unserer Technologie und unserer Wissens. Doch Erde birgt noch in der Verziffis. Die Erde birgt noch immer Geheimnis für uns Ziffer. Die Erde birgt noch immer Awareness für uns. In einem Zeitalter, in dem Satelliten jeden Bergskatien und Drohnen jeden Regenwald scannen, ist die Vorstellung, dass eine ganze Landschaft, vielleicht sogar ein ganzer Ökosystem, unter unseren Füßen verborgen bleiben konnte, gleichermaßen die Mut him, und das ist erfindend unterschiedlich, gedischigen versicherend. Sie erinnert uns daran, dass bei der Erforschung nicht nur darum geht, weiter oder schneller voranzukommen. Manchmal geht es darum, einen Weg zu finden, tiefer in Orte vorzudringen, die uns weiterstehen, uns hierher nicht so leicht preisgeben, uns hierher gelten und jetzt nicht so leicht preisgeben. Und nachher wir die kommen, desto mehr erkennen wir, dass die Geschichte nicht mit Druck, Dunkelheit oder versagender Technik endet, denn das Eis selbst ist nur ein Teil der Barriere. Darunter verbirgt sich noch etwas anderes, etwas, das uns zwingt, unser Verwogen beim Erkunden und sogar die Bedeutung des Erkundens selbst zu überdenken. Dorthin begeben wir uns als erstes in die Last von Milliarden Wintern, die auf einer Welt wartet, die wir noch immer nicht kennen. Hoch über den Landstrecken, wo Wälder sich wiegen und Flüsse ihre gewundenen Pfade graben. Jenche sitzt der Straßen, jenche hitzt der Eisengemmen Tundren, die sich bis zum Horizont erstrecken, gibt es einen Ort, an dem die Erde Theater einander halten scheint. Hier am Ende des Planeten wird das Wasser so fließen, die Luftwesen durchwärmen und selbst das Sonnenlicht verliert seine Kraft. Es ist ein Reich, das nicht von Chroniken oder Nationen beherrscht wird, sondern vom Eis selbst. ein uraltes, sich Wandel an des Königreich, älter als die ältesten Geschichten der Menschheit. Am wirklich zu verstehen, haben wir noch nicht unter die Gletscher des Nordpols vordringen können, müssen wir zuerst wissen, dass dieses Reiches begreifen. Denn es ist nicht einfach nur ein Ort, es ist eine Kraft. Es formt alles darüber und verbinde und alles darunter. Und es gibt seine Geheimnis nicht leicht preis. Wenn man sich den Nordpol vorstellt, liegt die Bermutung nahe, ihn als einen einzigen Punkt zu sehen, einen winzigen Flecken der Spitze der Weltkugel, einen Ort, an dem man eine Fläche hissen und ihn zum Ende der Welt erklären kann. In Wirklichkeit ist alles an der einfach zugehören konnte. In Wirklichkeit ist alles an der alles einfach. Der geografische Nordpol liegt gar nicht auf dem Festland, sondern mitten im arktischen Ozean, einer riesigen fleischessigen Wasser, die das ganze Jahr Biber von einem sich ständig, verändernd in Meeresmoos bedeckt ist. Anders als am Pol, wo der gewaltige antarktische kontinentale Scheide fest auf Fels ruht, schwimmt das arktische Eis. Es treibt mit den Strömungen, bricht und formt sich neu, schmilzt und gefriert wieder in einem Rhythmus, der sich Millionen von Jahren wiederholt. Das Eier ist nicht statisch, es ist lebendig, in Bewegung, atmet auf eine Weise, die unseren Vorstellungen von gefrorenen Landschaften widerspricht. Und diese Fluidität ist einer der Gründe, warum es so schwer ist, in das Eis einzudringen und zu erforschen, was darunter liegt. Dieser gefrorene Ozean ist von Land umgeben. Die nördlichen Ränder Nordamerikas, Europas und Asiens umschließen das arktische Becken wie eine schützende Mauer. Von Grönland bis Sibirien, von Alaska bis Skandinavien ragen Gletscher und Eiskappen ins Meer. Ihre gefrorenen verreifter Heiten in die präbenden Eisströmen. Manche dieser Gletscher sind gewaltig. Sie strecken sich über Hunderte von Kilometern und ewigen Tiefen, die in Kilometern messen werden, die in Kilometern schäfen, die in Kilometern der Heifen. Andere sind kleiner, aber nicht weniger bedeutend, speisen das Meeresbiss und prägen die arktische Umwelt auf Subtil, aber kraftvolle Weise. Zusammen bilden sie eine unterbrochene Exegrenz, die den Norden der Welt bedeckt, ein Esserlich, das sich ständig verändert, zusammenbricht, neu wabelt und wascht. Du gehst als Ausreich des Begegnen, ist nicht nur poetisch. In vielerlei Hinsicht verhält sich diese gefrorene Domäne wie ein lebender Organismus mit eigenen Systemen, Zyklen und Mustern. Das arktische Eis ist nicht einfach nur gefrorenes Wasser. Es ist eine dynamische Struktur, die ständig auf Veränderungen von Temperatur, Wind, Meeresströmungen und sogar Planetenbewegungen reagiert. Im Winter erhunte sich das Meer heiß dramatisch aus und bedeckt fast 14 Millionen Stücke hoch kürzer als der hafthibolische Kontinent. Im Sommer sieht es sich gedicht und schrumpft auf etwa 4 bis 5 Millionen Square. Doch selbst in diesen dunsten Phases bleibt das Eisig oft mehr Meter tief und besteht aus Schichten von Schnee und gefrorenem Schmelzer, die das darunterliegende Meereis sichern. Mit der Zeit kann das Nähreis der Meerjahre sitten, überdauern und dicker, härter und undurchdringlicher werden. Dieses Meerreich ist, wie Fischnaftler es nennen, ist eines der größten Hindernisse für Sydney Socheten Hindernisfür, die darunterliegenden Erfahrungskraften zu erweitern Gefahr. Unterhalb der Oberflächenschicht wird die Komplexität noch größer. Der arktische Ozean ist keine eintölige Wasserfläche, sondern eine zergiftete Meereslandschaft aus Rücken, Becken und submarinen Plateaus. An seiner tiefsten Stelle fällt Berghof auf Grund. Man hat mein in das Frambecken aber Der Rücken, ein Unterwassergebirge, verläuft wie ein Rückgrat über die Nordpol und teilt den Ozean in zwei große Becken. Das Suchen von in Eis- und Meeresbodentopographie schafft Reichen, in denen Eis zu gewaltigen veröffentlicht ist, Gebiete, in denen Schmelzer unter der Oberfläche schammelt und bergig, in denen das Meer in langsamen, kraftvollen Girbelt und Grodelt, die Strukturen der Komplexität der Erforschung des Untergrunds unterdrückt in Ibigei. Es geht nicht einfach darum, senkrecht und ten zu bauen. Jeder Mieter ist anders als der Überliegende, geformt von Kräften, die wir erst allmählich erfassen, und dann ist da noch das enorme Gewicht. Es mag sehr lächerlich nannte, wenn man einen Eiswürfel in der Hand hält, aber im Maßstab von Gletschern und Eisschilden ist es unvorstellbar schwerer. Jeder Quadratmeter Gerätes wiegt etwa 900 Kilometer dicht. Multipliziert man das mit Hunderten oder Tausenden von Metern, wird der Druck immens. Der grönlandische Eisteil, der einen Großteil der arktischen Eislandschaft dominiert, enthält genug Eis, um den globalen Meeresspiegel um mehr als 7 Meter steigen zu lassen. Sollte er vollständig dickschmelzen, das sind Billionen Tonnen gefrorenes Wasser, die auf das darunterliegende distant rote Fälle und Becken formen, Berge so Schlamm sammeln und alles, was darunter liegen, und wechselbarem Gewicht entschließen. Dieser Druck verändert die physikalischen Eigenschaften von Wasser und Gestein grundlegend. Er lässt Eis in seiner Basis schmelzen, selbst wenn die Oberfläche weit unter dem Gefrierpunkt bleibt. Er formt das Grundgestein und lenkt das Grundwasser um. Er schafft Gasflossenberge. In der flüssiges Wasser, in wohliger Dunkelheit, über Deltausende hinweg von der Oberfläche abgeschnittenen bestechen kann. In diesen abgeschlossenen Bergen liegen einige der großen Geheimnisse der Gakt des Bergen. Wissenschaftler vermuten, dass sich unter dem grönlandischen Eisenjeiton möglicherweise auch unter Teilen des Meereises Netzwerke Schublazzi Allergien und Flusses befinden. Dies verborgenen Wasserwegs transportieren vermutlich Schmelzwasser von der Basis des Eisdejodes zum Ozean. Fäden es in Fließgeschwindigkeit und beeinflussen so sein Begeht und beeinflussen zu seiner Bewegung. Einige beherbergen möglicherweise auch mikrobielle Ökosysteme, die sich in wohliger Isolation entwickelt haben und von Mineralien aus dem Grundgestein und Chemistein und Chemikalien anstatt und chemischen Energiequellen anstatt von Sonnenlicht genährt werden. Diese Ökosysteme könnten, falls sie existieren, einen Einblick in die Überlebensmöglichkeiten von Leben auf issigen Monden industriell im Sonnensystem geben, Orte wie Europa und Enceladus, wo Ozeane und Diameterstichten eingeschlossen sind, diese Jossen sind erschlossen. Durch die Entdeckung dieser Vergehen. Sehen ist hier schon schwierig genug. Sie zu erreichen und ganz andere Herausforderungen. Überhaupt einen solchen Erkundungsversuch zu unternehmen. Sind Wissenschaftler auf eine Reihe von Technologien angewiesen, die unter extremsten Bedingungen funktionieren müssen. Satelliten, Radar, Alimeter, Kanderwindsicher, Veränderungen der Eisoberflächen hoch erfassen und so auf flüssiges Wasser tief darunter Interwurten hindeuten. Luftgestütztes Sicherradar kann die inneren Schichten von Gletscherartigen von Blechernatien verborgene Strukturen solcher Motoren sowie mögliche Seinrichtungen sein. Sichern oder schon können die Eckelswan-Schauern der Heiß und Gestein verfolgen und Hinweise auf das liefern, was sich darunter befindet. Doch diese Instrumente haben ihre Grenzen. Sie können uns sagen, dass da etwas ist. Sie können uns nicht sagen, was es ist, dafür müssten Würmer, das Bochen durch eine sich bewährte, Westgebänder und ständig verändernde Eismasse ist eine so schwierige Aufgabe, dass selbst die Fortschrittspolar Forschungsdienste sie mit höchster Vorsicht angehen. Um das Ausmaß dieser Herausforderung zu verstehen, lohnt sich ein Blick auf die bisherigen Arbeiten in der Antarktis. Am Fetus in dieser zu Gletschern sie unter fast 4 Kilometern ist es bohrten russische Wissenschaftler jahrelang vorsichtig dorthin. Dabei kombinierten sie mechanische und thermische Verfahren, um das Eis zu durchdringen, ohne das darunter liegende Wasser zu verunreinigen. Doch selbst dann erlitt das Projekt immer wieder das Projekt. Die Bohrschächte vorhanden, gerade versagten in der eisigen Kälte und die Sorge eine Contamination verzögerte den Verlauf lang. 2012 erreichte das Time schließlich den See. Doch selbst dieser Vorwurf warf mehr Fragen auf, als beantwortete. Die aus dem Bohrloch entnommenen Proben lieferten keine eindeutigen Ergebnisse, und die wahre Beschaffenheit des Ökosystems im Inneren ist weitgehend unbekannt. Wenn das Behandeln stabiles Kontradox von zu schwierig ist, wie viel schwieriger muss es dann erst in der Arktis sein, wo das Eis sehr dünner, aber weniger stabil ist, die Plattform schwimmt unter Stürmungen. Darunter Stürmungen des Strömungen darunter ständig Wechsel. Hinzu kommt die Komplexität der politischen und logistischen Gegebenheiten der Arktisforschung. Die Region grenzt an 8 Länder: Kanada, Dänemark oder Grönland, Finnland, Irland, Norwegen, Russland, Schweden und die Vereinigten Staaten. Jedes Land mit eigenen Gewaltsansprüchen, weltwirtschaftlichen und strategischen Interessen. Die Koordination der Forschung in diesem geopolitischen Umfeld ist oft genauso herausfordernd wie die Wissenschaft selbst. Die Finanzierung großangelegter Polarforschungsprojekte ist begrenzt und hart umkämpft. Die Feldzeiten sind kurz, oft beschränkt auf wenige Monate, mit relativ stabilem Wetter im Sommer, und jede Expedition erfordert immense logistische Unterstützung. Eisbrecher, Überschuldach des Meeresbahnen, Flugzeuge und Versorgungsgüter zu liefern, und ganze Teams von Generand, Wissenschaftlern und Hilfskräften, die bereit sind, in einer der unwirtlichsten Umgebungen Erde zu arbeiten. Jedes Kilogramm Ausrüstung muss Tausende von Kilometern geflogen oder verschifft werden. Jeder Tropfen Treibstoff wird sorgfältig rationiert. Jede Feder kann tödlich sein. Die Arktis selbst ist kein Suchen, uns verschworen zu haben. Die Umwelt ist unscheinbar und erbittlich gekaien. Jepilich ist es unhörbar unerbittlich. Die Temperaturen hier unter 50 degrees Celsius fallen. Stürmekonnten ohne Warnung auftreten, betwinden bieten nahe stark genug sind, Strukturen zu zerstören und Ausrüstung zu verstoren. Das Meer selbst kann unter den Füßen preset werden und sich verderben und sie Boden fressen. Plötzliche Öffnungen im Eis können Maschinen und Menschen gleichermaßen verschlingen. Im Winter hundert die Region monatlich lang, macht die Navigation zum Radspiel und Schulenergie mutslos. Im Sommer geht die Sonne nie unter, schmilzt die Oberfläche unter niemals. Der Fahrschlag ist ungerade im Eis verstaucht, und darunter setzt der Ozean seine langsame, kraftvolle Bewegung fort und drückt und dicht das Eis auf unvorhersehbare Weise. Es ist ein Ort der bedeutige Versuche, gewaltig und selbstlich. Verlatt und im ständigen Wandel und wirklich und durchlappen. Und vielleicht ist der größte Widerspruch von allen folgende. Trotz all seiner Feinstelligkeit ist die Arktis auch eine der wichtigsten Hürdelige. Ist die Arktis auch kein der wichtigsten Hürde. Ihr Eis reflektiert Sonnenlicht zurück ins Weltall reglich zu die globalen Temperaturen. Ihre Gewässer treiben Meeresströmungen an, die Wetter musste weltweit plagen. ihre Gletscherbögen riesiger, behalf der klimageschichte undokumentären Atemwusveränderungen in Schnee und Eisschichten, die Hunderttausende von Jahren zurückhalten. Und ihre Ökosysteme, so spärlich und vibrant sie auch sein mochten, sind lebenswichtige Glieder in der biologischen Kette des Planeten. Die Arktis ist nicht nur eine gefrorenes am Rande der Landkarte. Sie ist der Herzschlag des Klimasystems der Erde und ein Fenster in die Vergangenheit und Zukunft unserer Planeten. Es ist auch wichtig zu wissen, dass das arktische Eis sich sehr hoch, ihre Lat aber nicht ewig ist. Im Laufe geologischer Zeitreihe aromatisch veränderter Ramt. Wo Millionen von Jahren war die Arktis ist frei und von Warmwälden bettet. In anderen Seiten dehnte sich das Eis weit über seine heutigen Grenzen hinaus aus und bildete es Erde, die tief in die heutigen eisigen Sonnen reichten. Selbst in der wirklich schwächerkursen Zeitspanne der Menschheitsgeschichte hat die Arktis bedeutende Veränderungen durchgemacht. Während der letzten Eiszeit lag der Meeresspiegel mehr als 120 Meter. Niedergewaltige Gletscher erstreckten sich über weite Teile der Kugel. Mit der Erwärmung des Klimas zogen sich diese Gletscher zurück und hinterließen die Landschaft, die wir heute sehen. Heute verändert sich die Arktis erneut, viel schneller als zuvor in der aufgezeichneten Geschichte. Das Meer schmilzt. Die Gletscher ziehen sich zurück. Und das seit Jahrtausenden beste Hände. Empfindliche Gletschers entwanken, durch Erwärmungen machen die Erforschung des Untergrunds steigert Schwurzen des Untergletscher und jugeln zugleich schwer das Zeitfenster, zu erforschen, was darunter liegt, krönte sich während, obwohl sich unsere Möglichkeiten durch den Wurzellichen, durch den Wurzelingen langsam verbessern, die Dimensionen dieses eisigen Reiches wirklich zu erfassen, hilft es nicht als einen einzigen Ort, sondern als eine geschichtete Welt zu betrachten. An der Oberfläche befindet sich das treibende Meer, das sich ständig bewegt und bildet. Darunter liegt der Sivan. Sein Wasser ist in Schichten unterschiedlicher Salzgehalte und Temperaturgeschichte geformt von Strömungen, die das arktische Becken in sich langsam fließenden Strudeln umkreisen. Unter der Wasseroberfläche liegt der Meeresboden, geformt von tektonischen Kräften und bedeckt mit Sedimenten, die Geschichte vergangener Klimate bergen. Und über dem Land, das diesen Ozean umgibt, liegt der grönländische Eisstil und unzählige kleinere Gletscher, die mit ihrem unvorstellbaren Gewicht nach unten drücken, zusammenwirkende Schichten ein System, das gleichzeitig ein System, das gleichen einander verbindend und tiefet ist. Jede flüsterte die anderen, aber jede berte auch ihre eigenen Geheimnis. In diesem Labyrinth aus Eis, Wasser und Gestein liegen die Geheimnisse der Arktis verborgen. Und in diesem Labyrinth scheitern uns sie beforschen. Und in diesem Labyrinth scheitern dann sie bemühen, sie zu erforschen. So oft an der Oberfläche stehend, vergisst man leicht, wie viel darunter verborgen ist. Die Arktis erscheint leer, still, karg. Doch unter dieser Still verbirgt sich eine Komplexität, die jeden Regenwald oder Kohlenkonhochens macht. Subglaziale Kanäle transportieren Schmelzwasser über Hunderte von Kilometern und verbinden Verborgene, sie in Netzwerken, die wir kaum verstehen. Sedimente unter dem Eis könnten das Kommen und Gehen der Eiszeiten dokumentieren und Hinweise darauf bewahren, wie sich das Erdklima verändert hat und wie es sich erneut verändert hat und wie es sich erneut verändert. Und wenn in diesen versiegelten, dunklen Leben existiert, könnte es Antworten auf einige der tiefgründigsten Fragen der Biologie liefern. Wie entsteht Leben? Wie passt es sich an? Und wo im Versum könnte es sonst dann existieren, die sie hingeschlossen hossen westiert. Dausch sie bleiben unerreichbar, versiehe der Durchkräfte, die wir noch nicht beswingen können. Dieses Reich ist nicht nur abgelegen. Es widersetzt dich echte Forschung. Es bietet sich, du willst den Stand brauchen. Es bietet dich Schritt, wo wirst denn brauchen. Es gibt sich, wo wir still gemelzen bauchen. Es je mal habt all, was wir hinschicken, und lässt die Löcher, die wir graben. Es verbeidet sein Schatzen nicht hinter Mauern, sondern in sich selbst, in Schichten aus sich ständig veränderndem, schleifendem, fließendem, Schichten Werkzeugen und Techniken entziehen, die wir für Andacht zeigen entgegen entziehen, die wir für an eurem gebunden entwickelt haben. Und doch, trotz all seines Widerstands, sieht es uns immer näher. Denn unter diesen sich ständig verändernden Schichten verbirgt sich mehr als nur Wache. Gestern und heute es, dort liegt Gesichten, geschrieben in der Haste, in Druck und Dunkelheit. Historien, älter als die Menschheit, und vielleicht sogar Lebensformen, die nie die Sohn gesehen haben, wenn die tiefer in dieses gefrorene Life vordringen. Erkennen wir, dass es nicht nur darum geht, bessere Bohrer oder starke Roboter zu bauen. Es geht darum, sich mit den fundamentalen Gesetzen der Eich wie sich selbst auseinanderzusetzen, mit dem Gewicht, dem Druck der Bewegung, der ständigen Umgestaltung der Welt unter unseren Füßen. Und es geht darum zu dahin, wie diese Kräfte mit den von uns bauten Maschinen und den Maschinen interagieren. Denn unter der Oberfläche dieser eisigen Welt verbirgt sich eine Wahrheit, die sich seit Millionen von Jahren prägt. Eine Wahrheit, die alles beeinflussen wird, was wir dort unternehmen. Diese Wahrheit klar zu erkennen, müssen wir nicht nur die Oberfläche oder gar das Es selbst betrachten, sondern die Kräfte, die alles zusammenhalten und es so schwer durchdringbar machen. Werde mal auf dem Eis nahe dem Nordpol stehen und die Hand gegen die Oberfläche drücken, konnte man meinen, etwas Lautes zu berühren. Eis bricht unter Druck. Es schmilzt bei wer mehr. Es lässt sich mit bei mehr, es lässt sich mit bei einer Hammer zeigen oder mit einer Klinge berten. Es hübte schicksalblicken, vergänglich, etwas, das sich menschlichen Werkzeugen und Maschinen leicht erweichen lassen sollte. Doch unter unseren Füßen erstreckt sich diese dünne Schicht hinab in eine so gewaltige, so hoch und so in ewiglichem Maße aus gefrorenem Wasser, dass das Land darunter verbergt und die Form des Planeten selbst veränderte. Die Gletscher der Arktis sind nicht zart. Sie sind alte, monstrose Ansammlungen von Schnee und Druck, Schicht für viele Millionen von Winter aufgebaut. Und Erdgewicht ist einer der Hauptgründe. Helve ist einer der Hauptgründe, warum wir die Welt unter ihnen noch nicht wirklich erforschen können. Jeden Schneeflock, der jemals auf das Polareis gefallen ist, tracht zu diesem immensen Gewicht bei. Es beginnt mit etwas fast lächerlich kleinem, winzigen Kristallen, die lautlos vom Himmel herabrisseln, und spazieren verjauscht daher. Jochitsch dermei und Jahreszeiten, Hitenten gegeneinander wickten. Die meisten schmelzen, wenn die Sommerstonne zurückkehrt. Aber die schmelzen, werden Teil von etwas Größerem. Während sie sich aufzudirmen, wird der Schnee am Boden der darüber liegenden Schichten zusammenstückt. Sein zartes Gitterwerk bricht unter dem Gewicht zusammen, bis es sich in Fan verwandelt. Ein körniges Produkt zwischen Schnee und eisiges Produkt zwischen Schnee und Eis. Über Jahrhunderte mit so einer Himende. Ihr hat diese Fan so dichtem Gletscher was ängstlich hitigeimek war, vom Wind getragen zu werden, wird schwer genug. Kontinentiumsformen. Allende grünisch eisig Jahr, die größte Eismasse der Nordhalbkugel, ins halte Eismasse der Nordhalbkugel, ins halt etwa 2009 Billionen Kubikmeter gefrorenes Wasser. Das reicht aus, die gesamten, vereinigten Staaten mit über 300 Meter dickem Eis zu bedecken. Its weight is measured not in tons but in trillions of tons, and that weight does not sit still. Ice flows. It does not flow quickly, at least not in human terms. But over decades and centuries, it behaves less like a solid and more like an incredibly slow, viscous liquid. Under the relentless pressure of its own mass, glacier ice deforms and moves outward from its thickest points, creeping toward the sea in currents that carry rock and debris with them. This movement isn't uniform. It varies with temperature, bedrock friction, meltwater lubrication, and countless other factors. But no part of a glacier is truly stationary. Even the thickest ice, which might seem frozen in place, is creeping millimeter or centimeter each day. And the deeper you go beneath that ice, the more intense the pressure becomes, squeezing rock, water, and even the glacier itself into new shapes. For humans and machines trying to penetrate this frozen world, that movement is an enemy we have yet to conquer. It bends drilling shafts, closes tunnels, and crushes anything that lingers too long. To grasp just how overwhelming this pressure is, consider the numbers. For every 10 meters of ice above a point, there's roughly 1 atmosphere of pressure, about 14.7 pounds per square inch. That means that beneath 1,000 mm of ice, the pressure exceeds 100 atmospheres. At 3,000 mm, as at the base of parts of the Greenland ice sheet, the pressure surpasses 300 atmospheres, more than 4 to 400 lbs per square inch. Few materials on Earth can withstand such force indefinitely without deforming. Steel can bend, glass can shatter, even rock will yield and flow over geological time. At those pressures, water behaves differently too. Its melting point drops, allowing it to remain liquid even when temperatures are below freezing. That means at the base of a glacier where pressure is highest, liquid water often exists in thin layers or pockets, lubricating the ice above and helping it slide over the bedrock. This meltwater is vital to the glacier's movement, but it also creates unpredictable conditions for explorers. A drill can suddenly encounter liquid water after kiln of solid ice, destabilizing the borehole and threatening contamination of pristine subglacial environments. The pressure doesn't just act vertically. As the glacier flows outward, it exerts immense horizontal forces as well, grinding against the valley walls and the bedrock below. The base of a glacier is not smooth. It's a chaotic zone of rock fragments, sediments, and meltwater, all being dragged along under crushing weight. This process, called glacial erosion, has carved out some of the world's most dramatic landscapes. U-shaped valleys, fjords, and basins that were once buried beneath miles of ice. But it also means that the interface between ice and bedrock is constantly changing. Cavities open and close, water channels shift, sediment builds up and is swept away. For any machine attempting to operate in this environment, predictability is nearly impossible. A probe lowered into one channel might find it sealed off by refreezing water days later. A drilling shaft might emerge into a cavity that didn't exist when the project began. The glacier is always reshaping itself, always rewriting the landscape below. This constant pressure also changes the shape of the land itself. The Earth's crust, though seemingly rigid, is elastic on long time scales. When a massive glacier forms, its weight pushes the crust downward, depressing the land beneath it. This phenomenon, known as isostatic depression, can lower the surface by hundreds of meters. When the glacier melts, the crust slowly rebounds, a process called isoatic rebound, but it can take thousands of years. In places like Canada and Scandinavia, the land is still rising today as it recovers from the weight of ice sheets that melted at the end of the last ice age more than 10,000 years ago. Under the Arctic glaciers, this interplay between ice and rock is ongoing. As the ice thickens and thins, advances and retreats, it flexes the crust below, altering groundwater flow, creating new channels, and reshaping the very foundations of the landscape. That means the world beneath the ice isn't just hidden, it's alive, dynamic, and constantly changing under forces far beyond our control. It's not only the land that feels this pressure, the ocean beneath the Arctic sea ice is also affected. Sea ice might seem thin compared to the Greenland ice sheet, but it still exerts significant weight over vast areas. That weight pushes down on the water below, altering currents and mixing patterns. Combined with the pressure from the glaciers that spill into the sea, it shapes the circulation of the Arctic Ocean itself. This circulation in turn influences the distribution of nutrients, the formation of deep water masses, and even global climate patterns. The Arctic is a crucial engine in Earth's climate system, and the weight of its ice is one of the pistons driving that engine. Any attempt to explore beneath it must contend not only with the pressure of the ice itself, but with the ocean. It helps shape a dynamic, powerful body of water that is as much a part of the system as the ice above it. For the machines we design, this pressure is more than a nuisance. It is a fundamental barrier. Traditional drilling equipment is built for rock, not ice. It's designed to bore through relatively stable materials under predictable conditions. In ice, everything is different. The material flows, it melts and refreezes. It exerts pressure in unpredictable ways. Drill shafts can buckle under the stress. Boreholes can close as the ice flows around them. Melt water can refreeze above the drill bit, trapping it deep within the glacier. And even if the equipment survives the journey downward, the conditions at the base, crushing pressure, unpredictable water pockets, unstable sediments can render it useless. Building machines that can operate reliably in these conditions requires not just stronger materials, but entirely new approaches to engineering. Even the most advanced robotic probes face similar challenges. Autonomous underwater vehicles designed to explore beneath ice must withstand immense pressure while navigating through complex shifting environments. Their hulls must be strong enough to resist crushing forces, yet light enough to allow for mobility. Their sensors must function in conditions of near total darkness and intense cold. Their power systems must operate reliably even as temperatures plunge and pressures plunge. And perhaps most challenging of all, they must do all of this without direct communication. Radio waves can't penetrate thick ice, and acoustic signals degrade quickly, leaving the robots largely on their own once they enter the under-ice environment. A failure deep beneath a glacier doesn't just mean the loss of expensive equipment, it means the loss of data, of progress, of years of preparation and planning. The pressure also poses a risk to what we're trying to study. If subglacial lakes and ecosystems exist beneath the Arctic ice, they have evolved in conditions that are almost entirely sealed off from the surface. Introducing even a small amount of contamination could irreversibly alter those environments. But sterilizing equipment for use under such pressure is extraordinarily difficult. Materials that are sterile at the surface may be compromised under hundreds of atmospheres of force. Fluids used in drilling can behave unpredictably, expanding or contracting in ways that create pathways for contamination. Even the act of drilling itself, the heat generated, the vibrations produced can disturb delicate environments. Balancing the need to explore with the need to protect these pristine systems is one of the greatest ethical and scientific challenges we face. It's easy to underestimate just how much time is embedded in that pressure. Each layer of ice represents a winter, a season of snow that fell and never melted, compressed into the fabric of the glacier. In some places, the ice at the base of Greenland's sheet is more than 1 million years old. That means the water trapped beneath it has been sealed away since before modern humans existed. The pressure we encounter there is not just physical, it's temporal. It's the weight of countless winters pressing down season after season, century after century, until the past itself becomes a barrier. Every attempt to penetrate that barrier is an attempt to move through time, to reach back into Earth's distant history and touch a world that has been untouched for longer than we can comprehend. And yet, the weight is not constant. Climate change is reshaping the Arctic, altering the balance of ice and water and changing the pressures beneath the surface. As temperatures rise, glaciers thin and retreat, reducing the weight they exert on the land below. This can trigger isostatic rebound, altering drainage patterns and potentially exposing subglacial environments to new conditions. It can also destabilize ice sheets, accelerating their movement and increasing the frequency of calving events where massive chunks of ice break off into the sea. These changes make exploration even more complex. A site chosen for drilling might become unstable before the project begins. A channel mapped one year might be gone the next. The very weight that has preserved these hidden worlds for millions of years is now shifting sometimes faster than our technology can adapt. This shifting weight also carries global consequences. As glaciers melt and lose mass, they contribute to rising sea levels, reshaping coastlines and threatening communities thousands of kilometers away. The meltwater they release alters ocean salinity and circulation, influencing weather patterns and marine ecosystems. The pressure they relieve on the Earth's crust can even trigger earthquakes and volcanic activity, subtle reminders that the cryosphere and the geosphere are deeply interconnected. Exploring beneath the Arctic ice isn't just about curiosity. It's about understanding processes that affect the entire planet. But those processes are governed by forces far greater than us, forces measured in millions of winters and trillions of tons. And so the weight of 1,000,000 winters remains one of the most formidable barriers between us and the world beneath the Arctic ice. It crushes our machines, distorts our measurements, and reshapes the landscape faster than we can map it. It hides water where we don't expect it, and seals it away where we hope to find it. It preserves ancient ecosystems while threatening to destroy them if disturbed. It is not a simple obstacle we can drill through or melt away. It is a force that defines the environment itself, shaping everything that happens beneath the ice and everything we try to do within it. But understanding that weight and learning how to work with it rather than against it is key to unlocking the secrets beneath the glaciers. It forces us to rethink how we design our tools, how we plan our missions, and how we imagine exploration itself. It reminds us that the Arctic is not an empty void waiting to be filled with our discoveries. It is an active, dynamic system with its own rules, its own rhythms, and its own immense inertia. And as we push deeper into its frozen heart, we begin to see that the problem is not just the weight pressing down from above. It is also the darkness that lies beneath, a darkness that has never known sunlight, never felt warmth, and holds within it mysteries older than memory itself. A darkness that will shape everything we do next. Far below the frozen skin of the Arctic, where no sunlight has ever reached and no eye is ever seen, there is a darkness that does not simply exist. It endures. It is older than the first stories humans ever told, older than the earliest tools carved from stone, older even than the landscapes that lie buried beneath it. It has been there since before ice covered this part of the world, before the continents settled into their current shapes, before mammals walked the earth. It is a darkness that has persisted unbroken for millions of years, sealed beneath the weight of ice and the indifference of time. And it is into this darkness that we would have to go if we ever hope to truly explore beneath the glaciers of the North Pole. It is not the kind of darkness we encounter when the sun sets, or when a light switch is flipped. Those are temporary, superficial darknesses, thin veils that can be pierced by a candle or a flashlight. This is a darkness so absolute, so total that it seems to erase the very concept of light. It is the product of kilometers of ice, each meter scattering, absorbing and blocking every photon that tries to pass through. Even in the clearest ice, sunlight penetrates only a few dozen meters. Beyond that, even the faintest trace of daylight disappears. Deeper still, the pressure increases. The temperature plummets and the ice becomes opaque, clouded with bubbles, sediments and layers formed by thousands of winters. By the time you reach the base, perhaps 2 or 3 kilometers below the surface, light is not just absent, it is irrelevant. There is nothing for it to reflect from, nothing for it to reveal. The darkness is not waiting to be illuminated, it simply is. This absence of light creates conditions that are almost alien. Human senses are built around light. Our eyes evolved to detect it. Our biology relies on it to regulate cycles of sleep and wakefulness. Our perception of space and movement depends on it. Without light, those senses falter. Even our machines struggle. Cameras are useless without artificial illumination. Lasers scatter unpredictably in cloudy ice. Sonar, often the best alternative, paints only crude outlines of what lies beyond. Every attempt to explore in this environment feels like groping through an endless void. Each piece of data incomplete, each measurement shadowed by uncertainty. It's not just that we cannot see, it's that the very tools we rely on to compensate for sight are limited, distorted, or defeated by the conditions. But the darkness is more than just a lack of light, it is also a product of isolation. The ecosystems beneath the ice, if they exist, have been sealed away from the surface world for hundreds of thousands or even millions of years. They have never seen the sun. They have never experienced day or night as we know them. Their rhythms, if they have any, are dictated by entirely different forces. The slow flow of meltwater, the chemical reactions between rock and water, the faint geothermal heat rising from below. In this darkness, life would have to exist without photosynthesis, relying instead on chemosynthesis, the extraction of energy from chemical reactions rather than sunlight. Such ecosystems exist elsewhere on Earth, most famously around hydrothermal vents on the ocean floor, where bacteria feed on minerals and support entire communities of organisms in total darkness. If similar life exists beneath the Arctic ice, it would represent not just a remarkable adaptation, but an entirely different way of being, one that has thrived beyond the reach of light for longer than our species has existed. This possibility is one of the most tantalizing reasons scientists want to reach these hidden worlds. The study of extreophiles, organisms that live in conditions previously thought uninhabitable, has transformed our understanding of life's resilience. Microbes have been found in boiling hot springs, inside nuclear reactors, deep within Earth's crust, and in Antarctic subglacial lakes buried under kilometers of ice. If life exists beneath the Arctic glaciers, it would add to this growing list of environments where biology defies expectations. More importantly, it would offer clues about how life might exist elsewhere in the universe. Icy moons like Europa and Enceladus are thought to have subsurface oceans beneath thick crusts of ice. If life can persist in the lightless, pressurized, chemically driven environment beneath the North Pole, it might also exist in the dark oceans of those distant worlds. Exploring this darkness is not just about understanding our own planet. It's about probing the boundaries of life itself. Yet, even if no life exists there, the darkness still holds secrets worth pursuing. The sediments trapped beneath the ice record a history of Earth's climate stretching back hundreds of thousands, perhaps millions of years. Each layer of sediment is a page in that history, recording changes in temperature, atmospheric composition, ocean circulation, and even volcanic activity. Accessing those sediments could help scientists reconstruct the story of Earth's past climate and improve predictions of its future. But those sediments are sealed beneath ice and darkness, protected by conditions that make them extraordinarily difficult to reach. Drilling through kilometers of ice is challenging enough. Extracting uncontaminated samples from a pitch-black pressurized and often waterlogged environment at the base is even harder. And even if we succeed, interpreting what we find is no simple task. The darkness preserves, but it also distorts. Layers can be disturbed by the movement of the ice above. Sediments can be mixed by meltwater flows. Signals can be lost or altered. Each sample is a puzzle, a fragment of a story written in a language we're still learning to read. The darkness also shapes the physical environment in ways that complicate exploration. In the absence of sunlight, temperatures remain consistently low, often far below freezing. The ice above insulates the base, trapping geothermal heat and creating a delicate balance between freezing and melting. Small changes in temperature or pressure can shift that balance dramatically. A slight increase in heat might create a meltwater channel where none existed before. A small decrease might freeze a passage shut. These changes can occur unpredictably and can render carefully planned exploration efforts useless. A borehole that reaches liquid water one year might encounter solid ice the next, A meltwater channel mapped by radar might have vanished by the time a probe arrives. The darkness hides these changes from us, leaving us to infer them from indirect evidence and guesswork. And then there's the psychological dimension of darkness, something we don't often consider, but which matters deeply in environments like this. Humans are not built for absolute darkness. Even in the deep ocean, bioluminescent organisms provide faint glimmers of light. Beneath the Arctic glaciers, there may be no such light at all. For explorers and scientists working in these conditions, the absence of visual cues can be disorienting, even disturbing. Time loses its meaning when there's no sunrise or sunset. Space becomes abstract when there's nothing to see. Machines, too, face challenges in this sensory vacuum. Navigation systems that rely on visual landmarks become useless. Cameras designed to detect light must rely on artificial illumination, which can alter the environment and affect the very things we're trying to study. Even sonar, which uses sound instead of light, struggles to provide high-resolution images in the complex shifting geometry beneath the ice. This sensory deprivation is one reason why exploring beneath the Arctic ice is often compared to exploring space. Both environments are extreme, hostile, and utterly alien to human senses. Both require technology that can function without direct human control. Both demand careful planning and meticulous attention to contamination and safety. And both offer the possibility of discoveries that could transform our understanding of the universe. But there is one crucial difference. Space is empty. The darkness beneath the Arctic is not. It is filled with water, ice, sediment, pressure, and potentially life. It is a darkness that is alive in ways we can barely imagine, shifting, flowing, reacting, and evolving even in the absence of light. Some might ask why darkness matters. After all, we have technology that can create light. We have lamps, lasers, and sensors that can illuminate even the deepest ocean trenches. But the problem is not simply lighting the way. It's that light behaves differently in this environment. In water, light scatters and absorbs quickly, losing intensity and coherence. In ice, the scattering is even more pronounced, and impurities like air bubbles and sediments can bend or block light entirely. Artificial illumination might reveal what is immediately in front of a probe, but it cannot pierce the darkness beyond a few meters. And even when it does, it can change what we see. Light introduces heat, which can alter the delicate thermal balance of the environment. It can also affect chemical reactions or biological processes, potentially disturbing the very systems we want to observe in their natural state. The darkness, then, is not just an obstacle. It is a defining feature of the environment beneath the Arctic ice. It shapes everything that exists there, from the physical structure of the ice to the chemical composition of the water, from the behavior of any potential life forms to the preservation of ancient sediments. And because it is so absolute, it also shapes our ability to explore. We are creatures of light trying to navigate a world that has never known it. Every tool we build, every mission we plan must account for that fundamental difference. We must learn to sense without seeing, to map without light, to study without disturbing. That requires technologies and techniques we're only beginning to develop, and a mindset that embraces the unknown rather than trying to banish it with illumination. There's also something profoundly humbling about this darkness. It reminds us that not everything on Earth is accessible to us, that there are still places where our knowledge ends and mystery begins. In a world where satellites can map every mountain and drones can photograph every forest, it is easy to believe that nothing remains hidden. But beneath the Arctic ice, hidden in darkness older than memory, there is a realm that has never felt the touch of sunlight, never echoed with human footsteps, never been mapped or measured. It is a reminder that the Earth still holds secrets, and that some of those secrets lie not in distant galaxies or exotic planets, but right here beneath our feet. For scientists, that humbling realization is also a source of motivation. Every time we push a little deeper into that darkness, we learn something new about ice dynamics, about climate history, about the limits of life. Every failure teaches us how to build better tools. Every unexpected discovery reshapes our understanding of what's possible, and every unanswered question fuels the desire to go further. The darkness is not just a barrier, it is an invitation, a challenge from the Earth itself to see how far our curiosity and ingenuity can take us. But even as we learn to work within that darkness, we must also remember that it is not static. Like the ice above it, it changes. It shifts as the glaciers advance and retreat. It deepens as layers of ice build up. It thins as melting accelerates. It moves as channels open and close. The darkness that exists beneath the Arctic today is not the same as the darkness that existed 1,000 years ago, and it will not be the same 1,000 years from now. That means that every attempt to explore it is a race against time, a chance to capture a glimpse of a world that may soon be gone or transformed beyond recognition. And that leads us deeper still into the question of what lies within this darkness beyond the reach of light and the grasp of our current technology, because hidden in that void are not just sediments and water and rock. There may also be entire networks of subglacial rivers and lakes flowing unseen beneath the ice. There may be chemical processes at work that we have never observed. There may be forms of life that evolved in ways we have yet to imagine. The darkness hides them all, not out of malice, but simply because it is what it is, ancient, immense, and indifferent. And as we begin to imagine what those hidden worlds might look like, we find ourselves moving from the realm of the known into the realm of speculation, into the territory of the hidden oceans we dream of. Beneath the glaciers of the far north, in a place where light has never reached and sound moves slowly through dense frozen silence, there may be entire worlds of water sealed away from everything we know. They are not oceans in the way we imagine them when we think of the Pacific or the Atlantic. They do not roar with waves or sparkle beneath sunlight. They are oceans without shores, without tides, without a surface. They flow through tunnels and basins beneath kilometers of ice, trapped and forgotten, shaped by pressure and time. They exist, if they exist, in total darkness, hidden from the rest of Earth for hundreds of thousands or even millions of years. And they may hold secrets about the history of our planet, about the nature of life, and about the limits of exploration itself. Science call them subglacial lakes, but that term hardly does justice to what they might be. The word lake suggests something placid and contained, but beneath the ice, water is neither. Under immense pressure, even small amounts of heat from friction, from geothermal energy, from the weight of the ice itself, can melt the base of a glacier. That meltwater doesn't stay still. It flows into depressions, tarve channels through the sediment, gathers in pockets and basins, and forms networks that can stretch for hundreds of kilometers. Some of these pockets remain sealed for tens of thousands of years. Others connect to one another, creating entire hidden drainage systems beneath the ice. Some drain suddenly in massive floods that reshape the landscape below. Others may persist quietly, isolated and undisturbed, sealed beneath ice so thick that not a single molecule of their water has touched the atmosphere since long before humans evolved. We know these hidden oceans exist beneath Antarctica. Lake Vostok, the largest of them all, lies beneath nearly 4 kilometers of ice and spans more than 12,000 square kilometers, roughly the size of Lake Ontario. It has been sealed off from the surface for at least 15 million years. Over 400 other subglacial lakes have been identified beneath Antarctica, each with its own shape, depth, and hydrological behavior. In Greenland, scientists have identified more than 50 subglacial lakes beneath the ice sheet. The most are smaller than their Antarctic counterparts. And beneath the sea ice of the Arctic Ocean, though direct evidence is scarce, models suggest that similar pockets of meltwater could exist where pressure, geothermal heat, and topography allow it. These are the hidden oceans we dream of, not vast open expanses, but labyrinthine networks of water beneath ice, flowing unseen and untouched. What makes these hidden oceans so fascinating is not just their existence, but their potential. They're among the most isolated environments on Earth, sealed away from sunlight, shielded from atmospheric exchange, and protected from surface contamination. They may have remained stable for vast stretches of time. Within them, chemical reactions driven by minerals in the bedrock or by the slow decay of radioactive elements could provide energy. Microorganisms, if they exist, might thrive on that energy, forming entire ecosystems independent of the surface world. They would not rely on photosynthesis, which requires light, but on chemosynthesis, using chemical reactions to sustain life. This is how life thrives around hydrothermal vents on the ocean floor, where sunlight never penetrates and volcanic activity provides heat and energy. If life can do the same beneath glaciers, it would be living proof that biology can persist in darkness, isolation, and extreme pressure. Implications of that are profound. If life can exist beneath the Arctic glaciers, it strengthens the possibility that life could exist elsewhere under similar conditions. On Europa, one of Jupiter's moons, a global ocean is thought to lie beneath a crust of ice tens of kilometers thick. On Enceladus, a moon of Saturn, gazes of water erupt from cracks in its icy shell, hinting at a subsurface ocean below. Both moons receive little sunlight, and both are too cold for liquid water on the surface. Yet, beneath their icy crusts, heat from tidal forces and radioactive decay may sustain liquid water and possibly life. Studying subglacial lakes on Earth could offer a preview of what those extraterrestrial oceans might be like. They're analogues, models, test cases, ways to study how life might arise, evolve, and survive in environments far removed from sunlight and surface conditions. But these hidden oceans are not just interesting because of what might live within them. They're also archives of Earth's past. The sediments at their bottoms may contain records of climate change, volcanic eruptions, and even asteroid impacts stretching back millions of years. Trapped gases could preserve snapshots of ancient atmospheres. Layers of deposited material could reveal shifts in ocean circulation, ice sheet dynamics, and global temperature. Unlocking these records could transform our understanding of how Earth's climate has changed over geological time and how it might change in the future. But accessing them is extraordinarily difficult. The very isolation that makes these lakes valuable also makes them fragile. A single drilling operation could contaminate them, altering their chemistry or introducing microbes from the surface. A single miscalculation could collapse a channel or drain a lake entirely. Every attempt to reach these hidden oceans carries risks, and those risks increase with depth, pressure, and complexity. Part of what makes exploration so challenging is that these lakes are not static. They fill and drain over time, responding to changes in pressure, temperature, and ice movement. Some may remain stable for tens of thousands of years, while others drain and refill on timescales of decades or even years. These drainage events can have dramatic consequences. When a subglacial lake drains, it can release billions of liters of water in a matter of days, carving channels beneath the ice and accelerating the glacier's flow. These sudden floods, known as yakulps, can reshape landscapes and even impact sea level. For scientists, they also mean that a target chosen for exploration might not exist in the same form by the time they arrive. A lake identified by radar one year might have drained the next. A channel mapped in one season might have shifted course by the following. The hidden oceans beneath the ice are not frozen in time. They are dynamic, evolving systems, and that makes them both more interesting and more difficult to study. Another obstacle is the sheer inaccessibility of these environments. Drilling through kilometers of ice requires immense amounts of energy, precision, and patience. Traditional drilling methods, which rely on physical cutting or the circulation of drilling fluids, risk contaminating the environment or becoming trapped as the ice flows and refreezes. Thermal drills, which melt their way downward, face challenges of their own. They require enormous power and must prevent the water above them from refreezing and sealing the borehole. Even if a drill reaches a subglacial lake, retrieving samples without contamination is a delicate process. The water is under high pressure and may gush upward into the borehole, carrying sediments and microbes that could compromise the sample. Specialized systems must be used to capture water and sediment cleanly, maintain pressure conditions, and preserve the environment below. Because of these challenges, much of what we know about subglacial lakes comes from indirect evidence. Radar and seismic surveys reveal their outlines. Satellite measurements detect subtle changes in ice elevation that indicate filling and draining. In some cases, water from subglacial lakes emerges at the glacier's edge, carrying sediments and microorganisms that hint at what lies beneath. But these glimpses are incomplete. They tell us that the hidden oceans exist, but not how they function, what they contain, or how they change over time. They leave us with tantalizing hints but few definitive answers. And so the hidden oceans remain largely in the realm of imagination, places we dream about but cannot yet touch. That imagination has grown richer in recent years as scientists develop new technologies designed to reach these remote environments. One promising approach is the cryobot, a robotic probe that melts its way through ice using heat, often generated by a nuclear power source. Unlike traditional drills, cryobots do not require boreholes to remain open, and they can operate autonomously, carrying sensors and sampling equipment directly into the lake. Once there, they can deploy smaller robots or collect samples before returning data to the surface. Another approach involves hot water drilling, in which high-pressure jets of heated water melt a path through the ice. This method has been used successfully in Antarctica to access shallow subglacial lakes, and researchers hope it can be adapted for deeper Arctic environments. Advances in autonomous underwater vehicles also hold promise. These machines could enter subglacial lakes through narrow openings and explore them directly, mapping their interiors and searching for signs of life. Despite these advances, the challenges remain immense. Communication through thick ice is limited, making it difficult to control or retrieve data from robotic probes. Power is a constant constraint, both for drilling and for sustained exploration beneath the ice, and contamination remains a serious concern. Any mission must adhere to strict cleanliness protocols to avoid altering the pristine environments below. These constraints mean that exploration progresses slowly, often over decades. Each mission requires years of planning, testing, and refinement. Each attempt builds on the lessons of those before it, and each discovery, however small, brings us closer to the hidden oceans we seek. The dream of exploring these hidden oceans is not just scientific, it's also deeply human. There is something about the idea of vast, unseen worlds beneath our feet that captures the imagination. It reminds us that even on a planet we've mapped in exquisite detail, there are still places we do not know, places that have existed in isolation for longer than we have walked the Earth. It reminds us that exploration is not just about reaching distant planets or probing distant stars. It's also about looking inward into the hidden corners of our own world. The oceans beneath the Arctic ice are not remote in the way Mars or Europa are. They're here beneath our own planet's surface, waiting for us to find a way to reach them. And yet, perhaps part of their allure lies in their inaccessibility. There is something profoundly compelling about a mystery that resists us, that refuses to yield no matter how hard we try. It humbles us, reminding us that we are not masters of this planet, but participants in its ongoing story. It challenges us, pushing us to invent new tools, new methods, new ways of thinking, and it inspires us, fueling the imagination with visions of what might be waiting in the darkness. Strange ecosystems, ancient sediments, chemical processes that have never seen the light of day. These are the hidden oceans we dream of, and though they remain beyond our reach for now, the dream itself drives us forward. As we chase that dream, we begin to understand that exploring beneath the Arctic ice is not just about water or life or history. It's also about the tools we build and the limits we confront. Every attempt to reach these hidden oceans has taught us something about what our machines can and cannot do. Every setback has revealed a new challenge: pressure that crushes steel, ice that flows and refreezes, channels that shift and disappear. The Arctic seems determined to remind us that it plays by its own rules, and that to explore beneath its glaciers we must learn those rules and build accordingly. And so our story now turns toward the machines we've built, and the ways they've succeeded, failed, and adapted in the face of one of the most challenging environments on Earth. For all our ambition, all our restless curiosity, and all the centuries we've spent turning questions into discoveries, we are still fragile creatures trying to reach into places that were never meant for us. And nowhere is that fragility more obvious than in our attempts to send machines into the frozen underworld beneath the Arctic glaciers. Every bolt of steel, every circuit board, every meticulously engineered drill and probe is a testament to human ingenuity. And yet, in the presence of ice that weighs trillions of tons, water that moves unseen in darkness, and pressure that can crush a submarine like a soda can, our machines look clumsy, small, and profoundly mortal. They stand at the edge of a world we cannot enter ourselves, built to touch what we cannot touch, to see what we cannot see. And still, for now, that world mostly remains beyond their reach. We have been building machines to explore hostile environments for as long as we've had machines at all. Deep-sea submersibles that withstand crushing pressure, rovers that crawl across alien landscapes, spacecraft that endure the cold emptiness beyond our planet. But the environment beneath the Arctic glaciers is unlike any other, and the tools we've built for one extreme do not easily adapt to another. It's a place where ice behaves both like a solid and a liquid, where water flows under pressures hundreds of times greater than those at the surface, where communication is nearly impossible, and where everything, temperature, structure, chemical composition, changes constantly and unpredictably. A machine designed for the deep ocean cannot simply be lowered beneath the ice. A drill built to pierce rock cannot be expected to survive kilometers of shifting, deforming glacier. To explore this hidden world, we've had to design tools that are as specialized and resilient as the environment is hostile. One of the first tools humans ever used to peer beneath Arctic ice was the nuclear submarine. During the Cold War, American and Soviet submarines prowled beneath the polar ice cap, navigating blind through a maze of shifting flows and jagged keys. These missions were feats of engineering and navigation, proving that humans could travel beneath ice for extended periods. But even these immense, powerful vessels were limited. They traveled beneath sea ice, not beneath glaciers. They stayed in open water, far from the chaotic interfaces where ice meets land or rock. And though they could map the underside of the ice and gather data about the water column, they could not approach the places where the real mysteries lie. The deep pressurized zones beneath grounded ice sheets where subglacial lakes and rivers hide. Submarines, for all their power, are too large, too blunt, too ill-suited for the precision and delicacy that such environments demand. To go deeper, scientists turned to drilling. The logic was simple enough. If we cannot go beneath the ice from below, perhaps we can go through it from above. Drilling into glaciers is not new. Ice cores have been extracted for decades to study past climates, but drilling all the way through to the base is another matter entirely. It is slow, difficult, expensive work. The ice is not uniform. It changes composition, density, and temperature. As you descend, layers of compressed snow give way to ancient ice riddled with bubbles and sediments. Pressure increases steadily, and the ice begins to behave plastically, flowing around the borehole and threatening to close it. Traditional rotary drills, which work well in rock, struggle here. They rely on drilling fluids to carry coatings to the surface and prevent the borehole from collapsing. But those fluids risk contaminating the pristine environments below. They also require constant maintenance and careful temperature control to prevent refreezing. Even when they succeed, it can take years to drill a single borehole, and one mistake can mean starting over. Thermal drilling offers an alternative. Instead of cutting through ice, these systems melt their way downward using heated water or mechanical heaters to carve a path. Hot water drills have been used successfully in Antarctica, where they can melt through several kilometers of ice in weeks rather than years. They create clean, wide boreholes that can accommodate instruments and sampling devices. But even these systems have limitations. They require vast amounts of energy, often supplied by fuel that must be transported thousands of kilometers into remote polar regions. They must carefully manage refreezing water, which can seal the borehole or trap equipment, and they are limited by the unpredictable nature of the ice itself. Change in pressure or temperature can alter the melt rate. A hidden layer of sediment or a sudden influx of meltwater can redirect the drill. It is a delicate balance, and one that is often tipped by forces we cannot fully predict or control. To address the challenge of contamination, Scientists have developed sterile drilling techniques that minimize the risk of introducing foreign microbes into subglacial environments. These systems use specially treated drilling fluids, closed-loop circulation, and meticulous decontamination protocols for every piece of equipment. Even so, the risk remains. A single contaminant introduced into a sealed subglacial lake could irreversibly alter its chemistry or disrupt any ecosystem within. For this reason, many projects stop short of breaching the base of the ice content to study layers above it. But this caution comes at a cost. It limits our ability to directly sample the water and sediments that hold the most valuable clues. We stand just meters above the unknown, able to sense its presence but not to touch it. While drilling pushes downward from above, another class of machines approaches from below, autonomous underwater vehicles or AUVs. These robotic explorers are designed to operate beneath ice without direct human control, navigating through complex environments and collecting data as they go. Some are torpedo-shaped, built to glide long distances through water. Others are compact and maneuverable, capable of slipping into narrow crevices and tunnels. Equipped with sonar, cameras, chemical sensors, and even robotic arms, they can map the underside of the ice, measure temperature and salinity, and search for signs of life. AUVs have been used beneath Antarctic ice shelves and sea ice, where they have revealed complex networks of channels and cavities carved by meltwater. They've even ventured into subglacial cavities near glacier grounding lines, places where ice, water, and rock meet in chaotic shifting equilibrium. But even the most advanced AUVs face formidable obstacles beneath the Arctic ice. Navigation is one of the biggest challenges. GPS signals cannot penetrate water, let alone ice, and acoustic navigation systems are limited in range and resolution. That means AUVs must rely on dead reckoning, calculating their position based on velocity and heading, which accumulates errors over time. Without regular updates, they can drift off course. Communication is another hurdle. Radio signals cannot pass through thick ice, and acoustic signals degrade quickly, limiting bandwidth and range. Most AUVs must operate autonomously, following pre-programmed instructions and returning to a rendezvous point for data retrieval. If they become stuck, damaged, or lost, there is often no way to recover them. And beneath a glacier, where channels twist unpredictably, ceilings shift, and debris moves with the ice, the risk of losing a vehicle is high. Pressure poses yet another challenge. At depths of several kilometers, the weight of the overlying ice and water can exceed hundreds of atmospheres. AUVs must be built to withstand this pressure without deforming or leaking. Their sensors and electronics must be sealed and insulated against intense cold and crushing force. Batteries, too, must be capable of operating reliably in near-freezing water under immense pressure, a combination that can shorten their lifespan and reduce their capacity. Every gram of weight and every cubic centimeter volume must be carefully considered to balance strength, buoyancy, and endurance. And because missions beneath ice can last days or weeks without the possibility of resurfacing, AUVs must carry all the power they need from the start. There are no charging stations beneath a glacier. One of the most ambitious technologies proposed for exploring beneath polar ice is the cryobot, a self-contained robotic probe designed to melt its way downward through ice, carrying instruments with it. Unlike conventional drills, cryobots do not require a borehole to remain open. They move slowly, melting the ice ahead and letting it refreeze behind them. In theory, a cryobot could descend through kilometers of ice, reach a subglacial lake, and deploy instruments or even smaller robots into the water. It could collect samples, take measurements, and send data back through a fiber optic cable trailing behind it. Prototypes have been tested in glaciers on Earth, and NASA is exploring cryobot designs as potential tools for exploring icy moons like Europa. But cryobots face many of the same challenges as other machines: power, navigation, communication, and contamination. They require enormous amounts of energy to melt their way downward, and once they reach their target, retrieving them may be impossible. If they become stuck or encounter unexpected conditions, they cannot backtrack. They are one-way missions, brave but expendable, Hot water drills, AUVs, cryobots, each represents a different strategy, a different way of approaching the problem. But all of them share a common limitation. They must operate in an environment that does not want them there. The Arctic ice is not passive. It moves, shifts, flows, and refreezes. It responds to pressure and temperature in ways that can seal boreholes, crush vehicles, or alter the terrain mid-mission. The water beneath the ice is not static either. It flows through channels that can close or change course. It carries sediments that can clog sensors or damage equipment. It can surge suddenly if a subglacial lake drains or remains still for centuries. Every machine that enters this environment must contend with forces that are indifferent to its presence. Forces that can undo years of planning in moments. And yet, for all these difficulties, progress is being made. Each failed mission teaches engineers something new about how to build machines for these conditions. Each lost probe reveals a flaw that can be corrected. Each unexpected result points to phenomena we had not anticipated. The challenges are enormous, but they are not insurmountable. Advances in material science are producing stronger, lighter hulls that can withstand pressure and resist ice abrasion. Improvements in battery technology are extending mission durations. New navigation algorithms are reducing drift and improving autonomy, and innovations in communication from acoustic modems to fiber optic tethers are expanding the range and reliability of data transmission beneath ice. These incremental advances may not sound dramatic, but they are essential steps toward the day when we can truly explore the hidden world beneath the Arctic glaciers. There's also a growing recognition that no single machine will solve the problem. The environment is too complex, too varied for one tool to do everything. Instead, the future of under-ice exploration likely lies in systems, networks of complementary technologies working together. Hot water drill might create an access point. A cryobot might descend through the ice. An AUV might then enter the water and explore the lake or channel beyond. Each tool would play a role, each compensating for the limitations of the others. Such integrated missions will be expensive, logistically challenging, and technologically demanding, but they may be the only way to overcome the barriers that have kept the Arctic's hidden world beyond our reach. The machines we build are more than just tools. They're extensions of ourselves, our eyes, our hands, our curiosity made physical. When we send them into places we cannot go, we are in a sense reaching there ourselves. Every sensor reading is a glimpse into the unknown. Every image is a window into a world we have never seen, and every failure is a lesson, a step closer to success. It is easy to think of machines as separate from us, as cold, impersonal devices. But in truth, they are expressions of our deepest desire to know. And the under-ice world of the Arctic is one of the ultimate tests of that desire. Still, even as our machines grow more capable, the environment beneath the ice remains a formidable adversary. It is not simply the darkness, the cold, or the pressure that challenge us. It is the fact the ice itself is alive in a way that stone or steel is not. It flows, flexes, and reshapes itself. It turns passages into dead ends, opens new ones without warning, and crushes obstacles with the patience of time. It is a labyrinth that never stays the same for long, a maze carved by forces older and stronger than us. And to truly understand why our machines struggle, why exploration beneath the Arctic glaciers remains so elusive, we must step back and look at that labyrinth itself, the ever-hanging world that confounds us at every turn. Beneath the frozen ceiling of the Arctic, past the shifting sheets of sea ice and the mountains of glacial ice pressing relentlessly downward, there is a world governed not by politics, ambition, or human will, but by physics. It is an environment shaped by pressure, temperature, density, and gravity, in ways that defy our everyday experience. It is a place where water behaves like rock, where ice flows like liquid, where heat and cold meet in delicate balance, and where even the strongest materials humanity has ever built can buckle and break. It is a realm that does not care about our goals or our timelines. It obeys only the most fundamental laws of nature, laws that have shaped it for millions of years and that will continue to shape it long after we're gone. And it is those laws, more than any lack of technology or willpower, that stand between us and the hidden world beneath the Nordpol's glaciers. The first and most obvious of these laws is pressure. On the surface, atmospheric pressure is something we rarely think about. It is the weight of the air above us, roughly 14.7 lbs per square in, and we live within it so completely that it becomes invisible. But beneath kilometers of ice, pressure ceases to be a background condition. It becomes the dominant force shaping everything. For every 10 mm of ice, the pressure increases by about 1 additional atmosphere. At the base of Greenland's ice sheet, more than 3,000 means thick in places. The pressure can exceed 300 atmospheres, more than 4,400 lbs per square in. To put that into perspective, that is roughly the pressure you would experience 3,000 meters deep in the ocean, a depth that crushes unprotected submarines and warps solid steel. Even specialized deep-sea vehicles designed to withstand the weight of kilometers of water struggle under similar conditions. The ice above is not water. It is heavier, denser, and far less forgiving. This immense pressure alters everything, even the nature of water itself. Under normal conditions, water freezes at zero. But as pressure increases, that freezing point drops. At the base of a thick glacier, water can remain liquid at temperatures well below zero. This means that even when the ice above is solid and immovable, there can be layers of meltwater beneath it, thin films or larger pockets moving slowly between the ice and the rock below. This water acts as a lubricant, allowing the glacier to slide over the ground, accelerating its flow. It also creates subglacial rivers and lakes sealed away under immense weight. For scientists, this presents a dual challenge. On one hand, the presence of water is crucial. It hints at hidden ecosystems, geological processes, and records of past climates. On the other hand, its behavior under pressure is unpredictable. A drill might encounter ice one moment and water the next. A probe might enter a seemingly stable cavity only to have it collapse under shifting pressure. Even our best models struggle to predict exactly how meltwater will move or where it will collect beneath kilometers of ice. Pressure also affects the ice itself. Though it appears solid, glacier ice is not static. Under extreme pressure, it flows slowly, imperceptibly, but relentlessly. The molecules within it rearrange themselves, allowing the ice to deform and creep outward under its own weight. This flow is what drives glaciers toward the sea, carving valleys and reshaping landscapes as they go. But it also means that the ice is constantly moving, even deep below the surface. It is not a fixed barrier that can simply be drilled through and forgotten. It is a living, shifting mass that closes boreholes, bends drilling shafts, and crushes instruments. A tunnel dug into the ice may last only days before it begins to collapse. A sensor placed deep within it might be carried kilometers from its original position over the course of years. For exploration, this movement is a nightmare. It means that nothing stays where we leave it. Nothing remains stable for long, and nothing we build beneath the ice can assume the luxury of stillness. This movement is not uniform either. It is influenced by temperature gradients, ice thickness, topography, and the presence of meltwater. Warmer ice deforms more easily than colder ice. Thicker ice flows faster than thinner ice. Ice sliding over smooth bedrock moves differently than ice grinding over rough terrain. These variations create complex patterns of stress and strain within the glacier, leading to crevasses, shear zones, and differential flow. In some regions, ice may move only a few centimeters per year. In others, it may surge forward by meters in a matter of days. These sudden shifts, known as surges, can radically alter the structure of the glacier and the environment beneath it. A meltwater channel that existed yesterday may be sealed off today. A cavity that was once stable may collapse without warning. These unpredictable changes make long-term exploration beneath the ice extraordinarily difficult. Instruments must be designed to tolerate movement, withstand crushing forces, and survive even as the environment around them transforms. The crushing reality of physics extends beyond pressure and flow. Temperature, too, plays a decisive role in shaping the environment beneath Arctic glaciers, and it does so in ways that are often counterintuitive. Deep beneath the ice, the temperature is not as cold as one might imagine. The weight of the ice itself generates heat through friction as it grinds against the bedrock. Geothermal heat from Earth's interior seeps upward, warming the base from below. Together, these forces can raise temperatures near the base of the glacier to the pressure-dependent melting point, allowing liquid water to exist even when the surface temperature is far below freezing. But this delicate balance is easily disturbed. A slight change in ice thickness, a small variation in geothermal heat flow, or a shift in surface temperature can alter the thermal regime at the base, turning solid ice into meltwater, or vice versa. These changes can have cascading effects, influencing glacial movement, water flow, and even the stability of the entire ice sheet. This interplay of pressure and temperature gives rise to one of the most complex and least understood phenomena beneath glaciers: basal hydrology. The network of water channels, films, and cavities that forms beneath the ice is constantly evolving, responding to changes in pressure, temperature, and ice movement. These networks can drain and refill, merge and split, expand and collapse. They can transport meltwater from the interior of the ice sheet to the ocean, or trap it in isolated pockets for thousands of years. They can lubricate the base of the glacier, speeding its flow, or drain away, slowing it down. Understanding this hydrological system is crucial not just for exploring beneath the ice, but for predicting how the ice sheet will respond to climate change. Yet it is one of the most challenging aspects of glaciology to study. Direct observation is nearly impossible, and indirect methods, radar, seismic surveys, satellite measurements provide only partial, sometimes contradictory data. The physics is simple in principle, but bewilderingly complex in practice. The ice does not merely flow over the ground, it reshapes it. Under immense pressure, rock behaves differently too. It may fracture, deform, or even flow plastically over geological timescales. Glacial erosion grinds mountains into powder, carving deep valleys and basins. As the glacier moves, it drags rock and sediment with it, depositing them elsewhere and altering the landscape below. These processes create constantly changing conditions at the glacier bed. New obstacles, new channels, new sediments, all of which affect water flow and ice movement. They also complicate exploration. A drill that successfully penetrates the ice may encounter hard bedrock, loose sediment, or liquid water, sometimes within meters of one another. A probe designed for one set of conditions may find itself in a completely different environment minutes after deployment. The variability is immense, and the physics that drive it are unforgiving. Even the basic act of drilling through ice is governed by physics that work against us. As the drill descends, the pressure increases and the ice becomes warmer due to the geothermal gradient and the heat generated by the drill itself. This can cause meltwater to form around the borehole. If that water refreezes, as it often does in the colder layers above, it can trap the drill or seal the borehole shut. Preventing this requires careful temperature control and the circulation of drilling fluids. But those fluids must be chosen carefully to avoid contamination and to match the changing pressure and temperature conditions. Even then, the ice may deform around the borehole, narrowing it or causing it to close entirely. These challenges are not simply engineering problems. They are the direct result of the physical properties of ice under pressure, properties we cannot change, only work around. And then there is buoyancy, another fundamental force that complicates exploration. Subglacial lakes and water channels are often under pressure far higher than the atmospheric pressure at the surface. Breaching them can release that pressure suddenly, causing water to surge upward into the borehole. This can flood equipment, contaminate samples, and even destabilize the ice above. Conversely, introducing a probe or sensor into a high-pressure environment can cause it to implode if it is not built to withstand the force. The difference between success and failure can hinge on a fraction of a bar of pressure. The consequences of getting it wrong can be catastrophic for the mission and potentially for the environment itself. All of these factors, pressure, flow, temperature, erosion, buoyancy, are interconnected. They form a system that is both stable and dynamic, shaped by fundamental physical laws that we cannot ignore or override. We can build stronger materials, more precise instruments, and more sophisticated models, but the underlying physics remain the same. Ice will always flow under pressure. Water will always seek equilibrium. Heat will always move from warmer to colder regions. Gravity will always pull everything downward. These are the rules of the environment beneath the Arctic glaciers, and they are not negotiable. Our struggles to explore beneath the ice are in many ways struggles against these rules, or more accurately, struggles to work within them. Every engineering decision must account for them. Every engineering decision must account for them. Every mission plan must anticipate them. Every model must incorporate them. And even then, surprises are inevitable because the scale and complexity of the system amplifies small changes into large effects. A tiny shift in temperature can alter the structure of the ice. A small increase in meltwater can change the flow dynamics. A slight change in pressure can cause a cavity to collapse or a channel to open. The closer we look, the more we realize that the physics governing this environment are not obstacles to be overcome, but realities to be respected. This relentless obedience to physical law is why the world beneath the Arctic ice remains so resistant to exploration. It is not hostile out of malice. It is indifferent. It simply is what it is. A realm shaped by pressure, temperature, gravity, and time. Indifferent to our ambitions and impervious to our expectations. And that indifference is humbling. It reminds us that for all our power, we're still subject to the same laws as everything else in the universe. Our machines may be strong, but ice can crush them. Our instruments may be precise, but pressure can distort them. Our models may be sophisticated, but nature can still surprise us. Yet within that humbling truth lies a strange kind of beauty. The same physics that frustrate us are also the ones that have created this hidden world in the first place. They have shaped the glaciers, carved the landscapes, sealed away the water, and perhaps even nurtured life in isolation. They have written a story over millions of years, a story of ice and pressure, of water and rock, of flow and balance, and they continue to write it. Now, our attempts to explore beneath the ice are not attempts to conquer that story, but to read it, to understand the language in which it is written. And as we try to read it, we begin to see that the difficulty is not just in the forces themselves, but in how they change. The ice is not static. It is not a solid wall we can drill through and forget. It is a moving, shifting, evolving labyrinth that changes shape as it flows. The channels beneath it open and close, the cavities expand and collapse. The pressure builds and releases. It is a world in motion, a puzzle that rearranges itself as we try to solve it. And to truly understand why we cannot yet reach the hidden depths of the Arctic, we must look closer at that motion, at the way the ice itself moves and reshapes the landscape, beneath it, turning even the most carefully planned mission into a gamble against time and change. Beneath the Arctic's frozen crown, the ice is not a monolith. It is not a static, unchanging slab that we can drill through like stone and expect to find the same thing on the other side. It is alive in its own slow, inexorable way, a shifting labyrinth sculpted by physics and time, twisting and reconfiguring itself over centuries and even moments. It creeps forward under its own weight. It fractures and heals. It opens hidden passageways only to close them again. It stretches, flows, and reshapes everything beneath it, constantly redrawing the map we try to follow. And that motion, more than any lack of courage or technology, is why we still cannot truly explore the world beneath the glaciers of the North Pole. When we think of ice, we imagine stillness. We imagine frozen lakes and rigid blocks, crystalline and motionless. But a glacier is not like that. A glacier is a river of ice, slow, viscous, relentless. It moves under the pull of gravity, spreading outward from its thickest points, flowing downhill toward the sea. This flow is not visible to the naked eye in the moment. Stand on the surface and it will seem as unmoving as a rock. But watch over weeks, months, or decades and the change is undeniable. Creases widen, sakes tilt and collapse. Ice streams, fast-flowing corridors within the ice sheet, surge forward at speeds that can reach several meters per day. Even the most stable parts of the glacier creep forward by centime each year. enough to move mountains of ice across continents over the course of millennia. The causes of this movement are deceptively simple. Gravity pulls downward. Pressure builds as more snow accumulates on top. The ice deforms under its own immense weight, flowing outward like honey poured from a jar, though on timescales far beyond human perception. The pressure at the base of the glacier lowers the melting point of ice, allowing thin layers of meltwater to form. This water lubricates the interface between ice and rock, reducing friction and accelerating flow. In places, geothermal heat seeps up from Earth's interior, melting more ice from below and feeding the water system, and the glacier itself grinds against the bedrock, generating frictional heat that further contributes to melting. All of these processes work together in a feedback loop. More meltwater leads to faster flow. Faster flow generates more friction. More friction produces more meltwater. The glacier is not just moving, it is teaching itself how to move faster. But this movement is not uniform. It is complex, variable, and often unpredictable. Some parts of a glacier flow steadily for centuries. Others stop and start surging forward in sudden bursts before slowing again. These surges can be dramatic. In Alaska, the variegated glacier has been known to surge forward by more than 4 kilometers in just a few months, a pace more than 100 times faster than its usual flow. Such surges happen when water pressure builds at the glacier's base, temporarily lifting it off the bedrock and allowing it to slide forward. When the pressure drops, the glacier settles back into place and the surge stops. Similar surges have been observed in Greenland and other parts of the Arctic, and they can radically alter the glacier's internal structure and the landscape beneath it in a matter of weeks. A channel that existed before a surge may be crushed, a cavity may collapse. A subglacial lake may be drained or split in two. Everything we thought we knew about the terrain beneath the ice can change overnight. Even where flow is steady, it is not uniform across the glacier. Ice near the surface under less pressure tends to move faster than an ice deep below. Ice near the center of a glacier often flows more quickly than ice along the edges where friction with valley walls slows it down. These variations create internal stresses that fracture the ice-forming creases that can extend hundreds of meters deep. They also create shear zones where different layers of ice slide past one another at different speeds. These zones are sites of intense deformation where ice crystals stretch, rotate, and realign in response to the forces around them. The result is a complex, ever-changing internal structure, a labyrinth of layers, bands, and folds that reflect the glacier's history of movement. Any probe or drill descending through this structure must contend with zones of differing density, strength, and flow, each posing its own challenges. The base of the glacier is even more dynamic. Here, where ice meets rock, pressure is greatest, melting is most likely, and movement is most chaotic. Meltwater carves channels through the sediment, linking subglacial lakes into networks that drain and refill unpredictably. As the glacier slides over bedrock, it plucks chunks of rock from the ground, carries them forward, and grinds them into silt. This erosion deepens valleys and widens basins, altering the shape of the bed over time. It also creates obstacles for water flow, forcing channels to reroute and lakes to migrate. Sometimes the glacier seals these channels entirely, trapping water in isolated pockets that can persist for centuries. Other times, a sudden drainage event sends billions of layers of water rushing toward the sea, carving new pathways in days. This constant reshaping means that the subglacial hydrological system is not a static network, but a living, evolving labyrinth, one that we cannot fully map or predict. It's not just the ice and water that move. The ground beneath them does too. The immense weight of a glacier pushes down on Earth's crust, depressing it by hundreds of meters in some places. When the glacier thins or retreats, the crust slowly rebounds, a process called isostatic rebound, altering the slope of the land and the direction of water flow. Over time, this can shift the entire drainage system beneath the ice. Channels that once flowed north may begin flowing south. Lakes that once drained into one basin may spill into another. The glacier responds to these changes, adjusting its flow and reshaping its internal structure in turn. It is a feedback loop that unfolds over millennia, and we're only beginning to understand its complexity. For scientists and engineers trying to explore beneath the Arctic glaciers, this movement is a formidable obstacle. It means that no map stays accurate for long. A cavity identified by radar one year might be gone the next. A borehole drilled into a water channel might miss its target entirely if the channel shifts during the drilling process. Even instruments deployed successfully can be lost or damaged as the ice moves around them. Fiber optic cables can snap, sensors can be crushed, probes can be carried away from their intended locations. The glacier does not care about our plans. It moves according to its own rhythms, indifferent to the delicate strategies we design at the surface. Even more challenging is the fact that this movement occurs on many different time scales at once. Some changes happen slowly over centuries as ice flows and landscapes evolve. Others happen suddenly, surges, drainage events, collapses in hours or days. This combination of gradual and rapid change makes prediction extraordinarily difficult. Models that work well over decades fail to capture events that unfold in days. Instruments designed for long-term monitoring can miss the brief but significant episodes that reshape the environment. And because direct observation is so limited, we often don't know these changes have occurred until after they've happened. The labyrinth shifts silently in the dark, and we're left piecing together its movements from fragmentary evidence. Even the sea ice above the Arctic Ocean, though thinner and more transient than glacial ice, contributes to this complexity. Driven by winds and currents, it drifts across the ocean surface, piling up into ridges and splitting apart into leads. This motion exerts stress on the glaciers where they meet the sea, influencing how and where they carve, the process by which chunks of ice break off and form icebergs. Calving in turn can trigger surges in glacier flow or alter the drainage of subglacial water. It can open new pathways beneath the ice or close old ones. It can change the shape of the ice front, affecting how water circulates beneath it. All of these changes ripple through the system, altering the labyrinth below in ways that are difficult to predict. Climate change is amplifying this motion in ways we're only beginning to grasp. Rising temperatures are thinning sea ice and accelerating glacier melt, increasing the amount of meltwater reaching the base of the ice. This can lubricate the glacier-bed interface, speeding up flow and increasing the frequency of surges. It can also change the pressure dynamics beneath the ice, triggering drainage events and altering the configuration of subglacial water systems. Warmer air and ocean temperatures can undercut glaciers from below, causing them to retreat more rapidly and destabilizing the labyrinth beneath them. These changes are not uniform. They vary from region to region, glacier to glacier, and even year to glacier, and even year to year. But they all contribute to a system that is becoming more dynamic, more unpredictable, and more difficult to study. Technology struggles to keep pace with this motion. A radar survey captures a snapshot of the glacier structure, but that snapshot may be outdated within months. A probe designed to navigate a particular set of channels may find those channels gone or altered by the time it arrives. Drilling through moving ice is like trying to hit a target that is shifting in 3 dimensions, while the ground beneath your feet moves too. Even autonomous underwater vehicles, which can adapt to some changes, are limited by the data they have and the paths they can follow. And once a mission is underway, there is often no way to adjust in real time. Communication through kilometers of ice is too slow and unreliable. Decisions must be made based on models that are at best educated guesses. All of this creates a paradox for exploration. To understand the labyrinth beneath the ice, we need data, but to get that data, we need to place instruments within the labyrinth. And to do that effectively, we need to know how it moves, which we cannot fully know without data. It is a circular problem and one that can only be solved through incremental progress, repeated measurements, improved models, and missions that build on the knowledge of those before them. Over time, these efforts begin to reveal patterns in the chaos, regions of relative stability, cycles of drainage and refreezing, relationships between surface melt and subglacial flow. These patterns do not eliminate uncertainty, but they reduce it, giving us footholds in a shifting landscape. Yet, even as our understanding grows, the labyrinth reminds us of its power. It is not a puzzle we can solve once and for all. It is a living system that will continue to evolve long after we're gone. Its pathways will open and close. Its lakes will drain and refill. Its channels will twist and root. And each time we return, it will be different. This reality is both frustrating and exhilarating. It means that exploration will always be challenging, always uncertain, but it also means that there will always be something new to discover, some new mystery hidden in the ever-shifting ice. It is tempting to think of this constant movement as an obstacle, something standing in the way of progress, and in many ways it is. It complicates planning, threatens equipment, and limits the data we can collect. But it is also part of what makes the subglacial world so fascinating. The labyrinth moves because the glacier is alive. Not alive in the biological sense, but alive as a system, responding to forces and feedbacks that shape our planet. That movement is what carves valleys, builds landscapes, and drives the flow of water beneath the ice. It is what links glaciers to the oceans and the climate to the cryosphere. It is what makes the Arctic not just a frozen wasteland, but a dynamic, evolving part of Earth's system. And as the labyrinth shifts, it draws us deeper into another layer of complexity, the influence of a changing climate on everything that happens beneath the ice. The glacier's motion is not just a product of internal forces, but also of external ones. From rising temperatures to shifting ocean currents, the climate's hidden hand reaches into the labyrinth, altering its shape, accelerating its flow, and changing the conditions beneath it in ways we're still trying to understand. If the moving ice itself weren't enough to challenge us, the atmosphere above it ensures that the labyrinth will never stay the same for long. And so, to understand why we cannot truly explore the world beneath the Arctic glaciers, we must look beyond the ice and into the broader forces reshaping it from above. High above the Arctic's frozen labyrinth, far from the hidden rivers and sealed-off lakes beneath the glaciers, another force is at work, one that is slower than the tides and subtler than the wind, yet far more powerful than either. It is a force that shapes the thickness of the ice, the speed of its flow, the temperature of its base, and the patterns of water beneath it. It is a force that reaches deep into the frozen heart of the Arctic without ever touching it directly. That force is climate, and its hidden hand is everywhere. It dictates how much snow falls each winter and how much melts in the summer. It sets the temperature of the air above and the ocean below. It determines how ice forms, how it flows, how it breaks apart, and how it disappears. And as that climate changes, as it warms and destabilizes, it reshapes the labyrinth beneath the glaciers in ways that make exploration harder and more urgent than ever before. For most of human history, the Arctic's climate has been remarkably stable by our standards. It has swung between ice ages and interglacial periods over tens of thousands of years. Yes, but those changes unfolded slowly, giving the ice time to grow and retreat in long measured cycles. Glaciers advanced, carving valleys and pushing sediments before them. Then they melted, leaving behind moraines and reshaped landscapes. As they withdrew, subglacial lakes formed and drained and formed again. The labyrinth shifted, but it did so predictably in rhythm with the planet's orbital variations and slow changes in greenhouse gas concentrations. But in the last century, that rhythm has been broken. The Arctic is now warming more than twice as fast as the global average, and that rapid change is rewriting the rules that have governed this region for millennia. The most obvious effect of this warming is the thinning of the ice itself. Warm air temperatures melt ice from above, while warmer ocean waters erode it from below. The Greenland ice sheet, which contains enough ice to raise global sea levels by more than 7 mids, is losing mass at an accelerating rate. Satellite observations show that it is now shedding over 250 billion tons of ice per year, a figure that has more than doubled in just a few decades. Sea ice, too, is vanishing. Summer sea ice extent has declined by more than 40% since the late 1970s, and the remaining ice is thinner and younger, more prone to melting and breaking apart. These changes are not just surface phenomena. They reverberate downward, altering the pressure at the base of the ice, the temperature of the water beneath it, and the structure of the labyrinth below. As the ice thins, the pressure at its base decreases. This might seem like a small change, but in a system governed by delicate balances, even small shifts can have outsized effects. Lower pressure raises the melting point of water, potentially reducing the amount of meltwater at the glacier bed. That in turn can increase friction between ice and rock, slowing the glacier's flow in some places. But the opposite can also happen. Thinner ice is more easily influenced by variations in temperature and meltwater input, making it more sensitive to seasonal changes. Surface meltwater, once confined to shallow layers, can now penetrate deeper into the glacier through creases and muellers, vertical shafts that carry water from the surface to the base. When that water reaches the bed, it can lubricate the ice, reducing friction and speeding its movement. In some areas, this has led to a paradox. Even as glaciers thin, they accelerate, surging forward toward the sea and delivering more ice to the ocean. The influx of meltwater also changes the hydrology beneath the ice. In the past, much of the water at the glacier base came from geothermal heat and pressure-induced melting, slow, steady processes that produced relatively stable water systems. Now, sudden pulses of surface meltwater can flood the subglacial environment, raising water pressure, opening new channels and altering flow paths. These changes can destabilize subglacial lakes, triggering drainage events that reshape the labyrinth below. They can also cause fluctuations in glacial velocity, as variations in basal water pressure influence how easily the ice can slide. For scientists trying to explore beneath the ice, this means that conditions can change dramatically from one season to the next, or even from one week to another. A channel mapped in the spring might no longer exist by autumn. A cavity targeted for exploration might have drained or moved. The labyrinth becomes not just a puzzle, but a moving target. Warming air is only part of the story. The oceans that lap against the edges of the Arctic ice are warming too, and their influence is profound. As warmer waters flow beneath floating ice shelves and glacier tongues, they melt the ice from below, thinning it and destabilizing it. This undercutting can lead to calving events where massive chunks of ice break off and drift away as icebergs. These events in turn can destabilize the glaciers upstream, causing them to flow faster and thin more rapidly. In Greenland, many of the fastest moving glaciers terminate in fjords where warm Atlantic waters are intruding farther inland than ever before, accelerating their retreat. This ice-driven melt is particularly difficult to predict and control because it depends on large-scale ocean circulation patterns that are themselves being altered by climate change. Ocean warming also affects the water beneath the ice directly. Warmer water can melt more ice at the base, increasing the volume and extent of subglacial water systems. It can change the temperature and salinity of these waters, altering their density and circulation patterns. These changes can influence where subglacial lakes form, how they drain, and how water flows beneath the glacier. They can even affect the chemistry of these environments, altering the availability of nutrients and energy sources for any potential life. For exploration, this adds yet another layer of complexity. Instruments designed for one set of conditions may encounter another. Models built on past data may no longer apply. The labyrinth we seek to explore is not just changing, it is changing in ways that are increasingly difficult to anticipate. The atmosphere too plays a subtler but equally significant role. As it warms, it holds more moisture, leading to changes in precipitation patterns. Some regions of the Arctic are seeing more snow, while others see less. In areas where snowfall increases, the added weight can thicken glaciers and increase pressure at their base, potentially enhancing basal melting and altering water flow. In areas with less snow, glaciers may thin more rapidly, reducing pressure and changing the dynamics in different ways. The timing of snow and melt also matters. Earlier spring melts can extend the melt season, increasing the amount of water reaching the glacier base. Late-season snowfall can insulate the ice, slowing melt and affecting temperature gradients. All of these factors interact in complex ways, influencing the structure and behavior of the labyrinth beneath the ice. Another consequence of a warming climate is permafrost thaw. Much of the Arctic's land is underlain by permafrost, ground that has remained frozen for thousands of years. As it thaws, It releases water into the hydrological system, which can influence glacier flow and subglacial hydrology. Thawing permafrost can also destabilize sediments, altering the landscape beneath and around glaciers. In some cases, this can open new pathways for water flow. In others, it can block existing channels. Either way, it adds another layer of variability to an already complex system. And because permafrost thaw is accelerating as the Arctic warms, its influence on the subglacial environment is likely to grow in the coming decades. The climate's hidden hand reaches even deeper into the very structure of the ice itself. As temperatures rise, the thermal profile of glaciers changes. Warmer ice is softer and deforms more easily, increasing the rate of flow. It is also more susceptible to crevasses, allowing meltwater to penetrate deeper. This combination can lead to faster, more dynamic glacier behavior, surges, collapses, and sudden accelerations that were once rare, but are becoming more common. These events can dramatically alter the labyrinth beneath the ice, routing water, reshaping channels, and changing the pressure and temperature conditions in which exploration must occur. They can also increase the frequency of iceberg calving and subglacial floods, adding new hazards for both natural systems and human activity. All of these changes, thinning ice, increased meltwater, warming oceans, shifting precipitation, thawing permafrost, are interconnected. They amplify one another in feedback loops that accelerate the transformation of the Arctic. Thinner ice is more vulnerable to melting, which exposes darker surfaces that absorb more heat, which leads to further melting. More meltwater lubricates glacier flow, increasing the delivery of ice to the ocean, which contributes to sea level rise and alters ocean circulation, which can bring more warm water into the Arctic. These feedbacks make the system not just dynamic but self-reinforcing, pushing it toward states that are increasingly unfamiliar and unpredictable. For those trying to explore beneath the glaciers, these changes pose profound challenges. The environment is no longer just hostile, it is unstable. Conditions that held for centuries can shift in a matter of years. Baselines that once seemed reliable are now moving targets. Equipment designed for one set of conditions may fail in another. Long-term plans may be rendered obsolete by rapid changes on the ground. And the very features we seek to study, subglacial lakes, channels, ecosystems, may disappear or transform before we can reach them. The labyrinth we are trying to map is being redrawn even as we plan our expeditions, yet this instability also offers opportunity. As glaciers thin and retreat, they expose areas that were once inaccessible. As subglacial lakes drain or connect to the surface, they offer glimpses into environments that were previously sealed away. As meltwater increases, it can carry sediments, chemicals, and even microorganisms from the base of the ice to the surface, providing indirect evidence of what lies below. These changes, while challenging, also open new windows into the hidden world beneath the Arctic. They remind us that exploration is not just about overcoming obstacles, but about adapting to new realities, and that those realities are always shifting. Perhaps most importantly, the climate's hidden hand forces us to confront the urgency of exploration. The world beneath the Arctic ice is not timeless. It is changing, and in some cases, it is disappearing. Subglacial lakes that have existed for millennia may drain in a single event. Ecosystems that have evolved in isolation may be exposed and altered. Sediments that record ancient climates may be eroded or redistributed. If we wait too long, we may lose the chance to study these environments in their original state. The same warming that makes exploration more difficult also makes it more necessary. We are racing against time and the clock is ticking faster than ever. But as much as climate complicates our efforts, it also connects them to something larger. The hidden world beneath the Arctic glaciers is not just a curiosity. It is part of the Earth's climate system, shaped by it and shaping it in turn. The ice that thins and retreats reflects less sunlight, warming the planet further. The meltwater that flows from beneath the glaciers influences ocean circulation, weather patterns, and ecosystems around the world. The sediments that emerge from beneath the ice record past climates and offer clues about future ones. To study what lies beneath the Arctic is to study the climate itself, its past, its present, and its future. And in that study, another question emerges, one that has driven much of our curiosity about these hidden realms from the beginning. If these isolated, shifting, pressured environments beneath the ice can exist at all, could they also harbour life? Could something be alive down there in the dark, cut off from sunlight and surface for thousands or millions of years? It is a question that pulls us deeper into the mystery and into the possibility that the darkness beneath the Arctic glaciers is not empty, but teeming with forms of life we've yet to discover. Deep beneath the Arctic's glaciers, far from sunlight, wind, and all the familiar rhythms of the surface, there may be worlds where life endures in ways we have barely begun to imagine. If such life exists, it is not life as we know it from forests or coral reefs or even the open ocean. It is life shaped by isolation, by darkness, by immense pressure, and by the absence of everything we think life needs. It is life that has never seen the sun, never breathed oxygen from the atmosphere, never known the changing of the seasons. It is life that whispers in the dark, sustained by forces so subtle and so alien to our everyday experience that it seems almost improbable. And yet, improbable does not mean impossible. If anything, the history of life on Earth suggests the opposite. Wherever there is water, energy, and time, life finds a way. For most of human history, we assumed life required sunlight. Plants convert light into chemical energy through photosynthesis, forming the base of nearly every food web on the planet. Animals eat plants, or eat other animals that eat plants. Even the microbes that underpin many ecosystems rely indirectly on sunlight. Take that light away, and life withers, or so we thought. That assumption began to unravel in 1977, when scientists exploring the Galapagos Rift discovered hydrothermal vents on the ocean floor, places where superheated water rich in minerals gushes from the crust. Around those vents thrived ecosystems utterly unlike anything we had seen before. Giant tube worms, clams, crabs, and countless microbes, all living in total darkness. These organisms did not rely on sunlight at all. Instead, they derived energy from chemical reactions, a process known as chemosynthesis. The microbes oxidized hydrogen sulfide and other chemicals in the vent fluids, producing energy and organic matter. Larger organisms fed on them or formed symbiotic relationships. Entire ecosystems flourished independent of the sun. That discovery changed our understanding of life's possibilities. It showed that life does not need light. It needs energy, and energy can come from many sources. Since then, scientists have found life thriving in places once thought barren, deep within Earth's crust, inside Antarctic subglacial lakes, in acidic hot springs, in radioactive waste, and in permafrost tens of thousands of years old. Everywhere we look, life seems able to adapt, persist, and evolve in conditions that would destroy most known organisms. This remarkable resilience is why many scientists believe that if liquid water exists beneath the Arctic glaciers, and there's every reason to think it does, then life may well exist there too. What might such life look like? Almost certainly, it would be microbial. The conditions beneath the ice, darkness, high pressure, low temperatures, limited nutrients, are not conducive to large complex organisms. But microbes are astonishingly versatile. They can metabolize a wide range of chemical compounds, survive extreme conditions, and persist for millennia with minimal energy. In subglacial lakes beneath Antarctica, scientists have detected microbial life in waters sealed off from the atmosphere for hundreds of thousands of years. Some of these microbes metabolize iron or sulfur from the bedrock. Others use hydrogen produced by chemical reactions between water and rock. Some appear to feed on dissolved organic matter that has been trapped beneath the ice since long before humans existed. These ecosystems are sparse compared to surface environments. A few thousand cells per milliliter of water compared to millions in the open ocean, but they are alive nonetheless, quietly cycling nutrients and energy in the darkness. If similar ecosystems exist beneath the Arctic glaciers, they could tell us a great deal about how life adapts to isolation and extreme conditions. They might reveal new metabolic pathways, ways of extracting energy from minerals or chemical gradients that we have never seen before. They might harbour ancient lineages of microbes that diverge from their surface, relatives hundreds of thousands or millions of years ago, offering a glimpse into evolution frozen in time. They might even show us how life could persist elsewhere in the universe. The icy moons Europa and Enceladus, both believed to harbour subsurface oceans beneath thick shells of ice, present conditions not unlike those beneath Earth's glaciers. Darkness, pressure, water, and chemical energy. If life exists there, it would likely resemble the microbial ecosystems beneath our ice sheets. Studying those ecosystems on Earth is therefore not just about understanding our own planet. It is also a rehearsal for searching for life beyond it. The idea of life beneath Arctic glaciers is more than just speculation. There are tantalizing clues that something might be there. Meltwater emerging from beneath Greenland's ice sheet contains microbial communities, some of which appear to originate from subglacial environments. Sediments beneath glaciers contain organic matter that could sustain microbial metabolism, chemical gradients. Differences in concentration of substances like iron, sulfate, and hydrogen exist in these environments and could serve as energy sources. And we know that liquid water does exist beneath many glaciers thanks to pressure, melting, geothermal heat, and friction. Combine water, energy, and time, and life's chances improve dramatically. The question is not whether life could exist there. It is whether it does, and if so, how it survives. Reaching these potential ecosystems, however, is extraordinarily difficult. The same barriers that make exploration of subglacial lakes challenging, pressure, temperature, contamination, and access apply here as well. Drilling through kilometers of ice without introducing surface microbes is a delicate task. Even the heat from a drill can change the local environment, melting ice, altering chemical gradients, or killing sensitive organisms. Sampling water or sediment without contamination is equally challenging. Instruments must be sterilized, sealed, and capable of withstanding extreme pressure and cold. And once samples are retrieved, they must be handled carefully to preserve any microbes they contain. Even with these precautions, distinguishing indigenous organisms from contaminants can be difficult. A single microbe introduced from the surface could multiply and obscure the native community. Despite these challenges, scientists have made progress. In 2013, a US-led team successfully drilled into Lake Willins, a subglacial lake beneath 800 miles of Antarctic ice, using a hot water drill sterilized with ultraviolet light and hydrogen peroxide. They recovered water and sediment samples that contained active microbial communities. These microbes were metabolizing iron, sulfur, and nitrogen compounds, evidence of a functioning ecosystem sealed away from the sun. Similar results have come from other Antarctic lakes and from sediments beneath Greenland's ice. Each discovery strengthens the case that subglacial ecosystems are not rare exceptions but widespread features of icy environments. If they exist beneath the Arctic glaciers, they could number in the trillions, forming a hidden biosphere beneath the ice. The implications of such a biosphere are profound. For one, it would expand our understanding of the limits of life. We already know that life can survive without sunlight, but subglacial ecosystems push that resilience even further. They show that life can persist in isolation for hundreds of thousands of years, sustained only by the slow trickle of chemical energy from rock and water. They suggest that life is not fragile and rare, but robust and adaptable, capable of thriving in conditions that seem inhospitable. That has implications for our search for life elsewhere. If microbes can survive beneath kilometers of ice on Earth, they might survive beneath the ice of Europa or Enceladus. They might even persist in the subsurface of Mars, where liquid water could exist deep underground. Such discoveries would also change how we think about Earth itself. Subglacial ecosystems, though hidden and sparse, are part of the planet's biosphere. They contribute to biogeochemical cycles, transforming minerals, recycling nutrients, and perhaps even influencing the chemistry of meltwater that eventually reaches the ocean. They are time capsules preserving lineages and metabolic strategies from Earth's distant past. They are laboratories showing us how life responds to isolation, scarcity and pressure, and they remind us that life is not confined to the places we find comfortable. It exists wherever it can, and sometimes where we least expect it. But life beneath the ice, if it exists, is also vulnerable. Its isolation is both its defining feature and its greatest protection. A single drilling operation could introduce foreign microbes that outcompete or disrupt native species. A small change in temperature or chemistry could alter the balance that has sustained life for millennia. Even the act of exposing these environments to light and air could have consequences we do not yet understand. That is why scientists approach subglacial exploration with such caution. They know that they are not just searching for life, they're intruding into ecosystems that have never encountered us before. They must tread lightly, balancing the desire to know with the responsibility to protect. There is also the possibility that life beneath the ice is not thriving but dormant. In such extreme conditions, microbes might spend most of their existence in a state of suspended animation, metabolizing so slowly that their generation times are measured in centuries. They might survive on trace amounts of energy, dividing once in a human lifetime or less. They might be relics from a time when the environment was different, clinging to existence as the world around them changed. If so, studying them could reveal not just how life survives, but how it endures, how it waits out hostile conditions and persists across geological timescales. It could show us that life's story is not just about flourishing, but about enduring even in silence. In the end, the search for life beneath the Arctic glaciers is about more than microbes. It is about our desire to understand what life is and where it can exist. It is about testing the boundaries of biology and expanding the definition of habitability. It is about connecting Earth's hidden biospheres to the search for life elsewhere in the universe. And it is about humility, the recognition that our planet still holds mysteries we have not solved, that there are still places untouched by human eyes, and that life may be thriving there without our knowledge. If we find life beneath the Arctic ice, it will change how we see our planet. It will remind us that Earth is still full of surprises, that its story is far from fully told. It will suggest that life is not a rare accident, but a natural consequence of the right conditions emerging wherever water, energy, and time converge. And if we do not find life, that too will teach us something about the limits of biology, the fragility of ecosystems, and the uniqueness of the surface world we inhabit. Either way, the search itself matters. It pushes our technology, our science, and our imagination to new frontiers. It connects disciplines, psychology, microbiology, chemistry, planetary science, into a shared quest. It turns the hidden depths of our own planet into a proving ground for future missions beyond it. And it transforms the Arctic from a frozen barrier into a place of possibility where whispers of life in the dark may yet become voices. Yet, as we peer deeper into this potential biosphere, we find that the story it tells is not confined to Earth alone. The conditions beneath the Arctic glaciers, darkness, pressure, isolation, chemical energy, are not unique to our planet. They exist elsewhere on worlds far from the sun, where ice hides oceans that may harbour their own forms of life. And so our gaze turns outward toward those distant places, and we begin to see the connection between Earth's hidden biospheres and the alien oceans we long to explore. The Arctic secrets are not just Earth secrets. They are mirrors of other worlds, and through them we may glimpse our place in the universe itself, far beneath the Arctic's glaciers, in those lightless realms where pressure crushes rock and water flows unseen. There is more than just the story of Earth. There is a reflection of something larger, a mirror held up to the cosmos. For all their remoteness, the hidden lakes, channels, and possible ecosystems beneath our polar ice sheets are not unique. The conditions that shape them, the cold, the darkness, the pressure, the isolation, the chemical gradients that sustain life without sunlight, are not confined to this planet. They exist elsewhere, scattered across our solar system and beyond, on worlds where ice hides oceans, where liquid water flows beneath frozen crusts, and where life, if it exists, must adapt to the same kinds of challenges that life would face beneath the Arctic's glaciers. In studying these hidden realms here on Earth, we are not just probing our own planet's secrets. We are rehearsing for exploration elsewhere, learning how to reach, understand, and protect environments that may hold answers to one of humanity's oldest questions. Are we alone? The most obvious of these extraterrestrial mirrors is Europa, one of Jupiter's 4 large Galilean moons. Slightly smaller than our own moon, Europa is a world of ice and rock, its surface etched with cracks and ridges that betray the movement of ice over liquid water. Beneath that surface, beneath ice estimated to be 10 to 30 kilometers thick, lies a global ocean containing more water than all of Earth's oceans combined. That ocean is kept liquid not by sunlight, but by tidal heating, the result of Jupiter's immense gravity flexing and kneading Europa's interior as it orbits. The result is a world with a vast, dark, pressurized ocean sealed beneath ice, an environment strikingly similar to the subglacial lakes and channels beneath Earth's glaciers, lakes and channels beneath Earth's glaciers. If life exists there, it would likely resemble the microbial ecosystems we think might exist beneath our own ice sheets, living off chemical energy from the interaction of water and rock or from compounds delivered through cracks in the ice. Enceladus, a small moon of Saturn, offers another mirror. Beneath its bright icy surface lies a global ocean as well, kept liquid by the same tidal forces that warm Europa. Unlike Europa, however, Enceladus gives us direct evidence of that ocean's existence. Through fractures near its south pole, it sprays plumes of water vapor, ice particles, and organic molecules into space, material that spacecraft like Cassini have flown through and sampled. Those plumes contain salts, simple organic compounds, and tiny grains of silica, all signs of chemical interactions between water and rock on the seafloor. They hint at hydrothermal activity, the same kind of activity that sustains life around Earth's deep-sea vents and might sustain it beneath our ice sheets. If microbial life exists in Enceladus's ocean, it may be chemically and structurally similar to the life that could exist beneath Arctic glaciers. And if we ever send a probe into that ocean, it will face many of the same challenges as a mission to Earth's subglacial lakes, penetrating thick ice, avoiding contamination, and surviving in a dark, pressurized environment. Even farther afield, other icy worlds beckon. Ganymede and Callisto, Jupiter's other large moons, are believed to harbor subsurface oceans. Titan, Saturn's largest moon, has a thick shell of ice overlying a deep ocean of water and ammonia. Pluto, once thought too small and cold to host liquid water, may have a subsurface ocean as well. And beyond our solar system, exoplanets and exomoons orbiting distant stars may host similar environments, though we cannot yet see them directly. All of these worlds share key features with the hidden realms beneath Earth glaciers: thick ice, liquid water beneath, chemical energy sources, and long-term isolation from sunlight. They are variations on a theme, and that theme suggests something profound. The conditions that make life possible beneath ice are not rare. They may be among the most common habitable environments in the universe. This realization has transformed how scientists think about the search for life beyond Earth. For much of the 20th century, that search focused on planets with surface conditions similar to ours. Warm, temperate worlds where liquid water could exist in lakes, rivers, and oceans under an atmosphere and sunlight. Mars, once wetter and warmer than it is today, was the prime target. Venus, before we understood its runaway greenhouse effect, was another. Even distant exoplanets are often judged by whether they lie in the habitable zone, the region around a star where liquid water could exist on the surface. But the discoveries of subsurface oceans on icy moons, and the realization that life can thrive without sunlight, have expanded that perspective. Habitability is not limited to the surface. It may be far more common beneath ice, shielded from harsh radiation and insulated against extreme temperatures. In this new vision of habitability, Earth's subglacial environments are invaluable analogies. They give us natural laboratories for studying how water interacts with rock in the absence of sunlight, how chemical energy can sustain ecosystems, how life adapts to pressure and isolation, and how microbial communities evolve in sealed environments over long timescales. They allow us to test technologies and techniques that could one day be used on other worlds. Drills that can penetrate thick ice without contamination. Autonomous probes that can operate in dark, pressurized water. sensors that can detect chemical signatures of life in hostile conditions, every mission to a subglacial lake. Every experiment beneath a glacier is not just an exploration of Earth, it is a dress rehearsal for Europa Enceladus and worlds beyond. This connection works both ways. The discoveries we make on other worlds also inform how we think about Earth's hidden environments. Cassini's detection of organic molecules in Enceladus's plumes, for example, highlights the importance of water-rock interactions as potential energy sources for life. Interactions that likely occur beneath Earth's glaciers as well. Models of Europa's ocean circulation help scientists understand how water might move beneath ice sheets on Earth, and the search for biosignatures, chemical, isotopic, or structural traces of life on other worlds, pushes us to refine our methods for detecting them. Here it teaches us to look for subtle signals in complex data, to distinguish between biological and non-biological processes, and to interpret evidence cautiously but creatively. The parallels between Earth's subglacial environments and extraterrestrial oceans also raise intriguing questions about life's origins. Some scientists believe that life on Earth may have begun not in shallow sunlit seas, but around hydrothermal vents on the ocean floor, environments rich in chemical energy, shielded from harmful radiation, and conducive to the formation of complex organic molecules. If life can begin in such places, then it might also arise beneath ice, where similar conditions exist. That possibility blurs the line between Earth-like and alien environments. It suggests that the distinction between the Arctic's hidden lakes and Europa's ocean may be one of degree, not kind, and it implies that by studying life beneath our own ice sheets, we may be glimpsing how life could emerge elsewhere, and perhaps how it first emerged here. This cosmic mirror also challenges how we think about exploration itself. Sending a probe through kilometers of ice on Earth is hard enough. Doing so on Europa or Enceladus, tens or hundreds of millions of kilometers away, is orders of magnitude harder. Communication delays make real-time control impossible. Power sources must be compact, reliable, and long-lasting. Instruments must survive years of travel through space before operating flawlessly in an alien environment. Sterilization is even more critical because contaminating another world with Earth microbes could destroy the very evidence we seek, and yet the basic principles are the same. A cryobot melting through Europa's ice will face many of the same challenges as one descending into a subglacial lake beneath Greenland. An autonomous underwater vehicle exploring Enceladus's ocean will rely on the same navigation and sensing technologies as one operating beneath an Antarctic ice shelf. Earth's glaciers are proving grounds, places where we can practice for the far more difficult missions to come. There is a poetic symmetry in this. The same environments that frustrate us here, the darkness, the pressure, the moving ice, the risk of contamination, are the very environments that may hold life elsewhere. The same problems we must solve to reach subglacial lakes are the ones we must solve to explore alien oceans. And the same questions we ask of the Arctic's hidden biospheres. How do they survive? What fuels them? How do they evolve? Are the questions we will ask on Europa, Enceladus, and beyond. In this way, Earth's most inaccessible environments become keys to the universe. They show us not just what is possible here, but what may be possible everywhere. This perspective also reframes our relationship with the Arctic. It is not just a remote, inhospitable region at the edge of the map. It is a bridge between worlds, a place where planetary science, biology, geology, and engineering converge. It is where questions about life on distant moons become questions about life on Earth, and where answers about Earth feed back into our search for life elsewhere. The Arctic's hidden realms remind us that exploration is not a straight line outward into space, but a loop, a dialogue between the near and the far, the known and the unknown. What we learn beneath our own glaciers shapes how we search beyond them, and what we find beyond them shapes how we look beneath our own. It is possible that when we finally penetrate the ice of Europa or sample the plumes of Enceladus, we will find no life there. It is also possible that we will find something astonishing, microbes swimming in darkness, drawing energy from rocks and minerals as their cousins may be doing beneath Earth's ice. Either outcome will teach us something fundamental about the universe. If life is absent, It will show us that the conditions beneath ice, while potentially habitable, are not always inhabited. If life is present, it will suggest that biology is not a rare accident, but a common outcome of the right conditions. Either way, the work we do beneath Earth's glaciers will have prepared us to understand what we find. And perhaps that is the greatest lesson the Arctic's hidden world offers us. That our planet is not isolated, its mystery is not unique. The same physics, chemistry and potential for life that shape our subglacial environments are at work across the cosmos. The same stories unfolding beneath Greenland's ice are unfolding beneath the ice of distant moons. The Arctic is not just a place, it is a model, a microcosm, a mirror in which we glimpse other worlds, and in that mirror we also glimpse ourselves, a species reaching outward, driven by curiosity, trying to understand not just where we are, but where we might go. As that mirror widens and deepens, it reveals something even more profound. The environments we seek to explore beyond Earth are not just distant targets. They are connected to our own planet by shared processes and histories. They remind us that Earth is part of a continuum, one world among many shaped by ice and water, darkness and energy. And as we turn our gaze back from those distant oceans to the one beneath our own polar ice, we realize that exploring them is not just about answering cosmic questions. It is also about understanding how fragile, how precious, and how fleeting our own frozen frontiers may be, and how much we stand to lose if we do not learn from them before they change beyond recognition. Even if one day we conquer the engineering challenges, master the physics, and build machines that can slip through the labyrinth beneath the Arctic glaciers as easily as a fish glides through water, there will still be a part of that world that we cannot and perhaps should not reach. Because beneath the ice, past the pressure and the darkness, past the rivers we cannot see and the lakes we cannot touch, lies not just a physical frontier, but a philosophical one. It is the realization that some mysteries are not meant to be solved completely, that some questions must remain partly unanswered if they are to retain their meaning. And this is perhaps the deepest truth about the hidden world beneath the North Pole's glaciers. It's not only a place we cannot fully explore, it is a place that in some profound sense we should never fully conquer. We are by nature a species that wants to know. Curiosity has driven every leap we've made, from the first tools to the first telescopes, from crossing oceans to walking on the moon. It has built civilizations and reshaped continents. It has sent machines to the edge of the solar system and uncovered the structure of DNA. And it is the same curiosity that pulls us northward into the cold and the dark, to ask what lies beneath the ice. We want to know what worlds exist beneath kilometers of frozen water. We want to know if life is there, how it survives, what it can teach us about ourselves and the universe. But curiosity, powerful as it is not the same as entitlement. Wanting to know does not mean we are meant to know everything. The line between exploration and intrusion is thinner than we like to admit, and beneath the Arctic glaciers, that line matters more than ever. For the ecosystems that may exist down there, if they exist at all, isolation is everything. They have evolved or persisted or endured without interference from the surface for thousands or even millions of years. Their chemistry, their balance, their very existence depends on that isolation. To breach it, even with the best of intentions, is to risk destroying what makes them unique. A single bacterium introduced by a drill bit could out-co-compete native microbes that have never encountered such a rival. A small change in temperature from the heat of our instruments could shift the chemistry of an entire ecosystem. A drop of drilling fluid could contaminate a pristine environment beyond recovery. These are not hypothetical concerns. They are real risks documented in every attempt to explore subglacial lakes and channels. And they force us to confront an uncomfortable question. Is knowledge always worth the cost? There is also the question of authenticity. A sealed subglacial lake is a time capsule, a record of conditions that may date back hundreds of thousands of years. It contains not just water and sediment, but information about past climates, about geological processes, about the evolution of life. Once we open it, we change it. Even if we are careful, even if we avoid contamination, The act of breaching that isolation alters pressure, temperature, and chemistry in ways that cannot be undone. It is like opening a tomb. Once the seal is broken, the contents are never quite the same. If we want to study these environments as they truly are, not as they become after we touch them, then we must accept that some part of them must remain beyond our reach. This tension between our desire to know and the need to protect what we seek to know is not unique to the Arctic. It is present wherever exploration pushes into untouched realms. It was there when we first sent probes to Mars, forcing us to grapple with planetary protection protocols to avoid contaminating a potentially habitable world. It is there in the plans to drill into Europa's ice, where any contamination could compromise the search for life. And it is there beneath our own glaciers, where the environments we wish to study may be irreversibly altered by the very act of studying them. These are not reasons to stop exploring, but they are reasons to proceed with humility, restraint, and a willingness to leave some mysteries partially intact. Humility is not a trait our species has always embraced. We like to think of the world as something to be mapped, measured, and mastered. We celebrate the moment we plant a flag, take a sample, or bring back a photograph. We mark progress in terms of what we have claimed. But beneath the Arctic glaciers, mastery is an illusion. The forces at work there, pressure, gravity, time, are older and stronger than anything we can build. The labyrinth beneath the ice is constantly reshaping itself, beyond our control. The possible ecosystems within it have evolved independently of us, beyond our influence. The best we can do is approach as guests, careful, temporary, and aware that we're entering a place that does not belong to us. There is value, too, in not knowing everything. Mystery has always been part of what drives us, but it is also part of what grounds us. It reminds us that the universe is larger and stranger than we are. It keeps us humble, curious, and cautious. It teaches us that our understanding will always be partial, that there will always be horizons beyond our reach. The hidden world beneath the Arctic's ice is one of those horizons. It is a reminder that even on a planet we have mapped and measured, there are still places untouched, still stories untold, still questions unanswered. That is not a failure. It is a feature of a living, changing world and of our relationship with it. And perhaps in a deeper sense, the mystery must remain, because it tells us something fundamental about life itself. Life thrives not just in the places we can see and measure, but also in the places that remain hidden. It is not confined to the obvious or the accessible. It persists in darkness, under pressure, in silence beyond our reach. That persistence is part of what makes life extraordinary, and part of what makes our planet extraordinary. If we were to pierce every glacier, drain every lake, and expose every hidden ecosystem, we might learn much, but we might also lose something precious. The knowledge that there are still corners of the earth where life, if it exists, does so entirely on its own terms. The Arctic itself seems to insist on this. Every time we get close to revealing its deepest secrets, it changes. Channels close, lakes drain, ice shifts, instruments are lost, missions fail. It is as if the labyrinth moves not just because of physics, but because the mystery itself resists us, demanding patience, caution, and respect. That resistance is frustrating, but it is also instructive. It reminds us that exploration is not conquest. It is a relationship, a dialogue between what we want to know and what the world is willing to reveal. And like any relationship, it depends on trust, patience, and boundaries. This perspective does not diminish the importance of exploration. On the contrary, it enriches it. It suggests that our goal is not to strip away every layer of mystery, to understand the world more deeply while leaving parts of it intact. It suggests that discovery is not always about possession, but sometimes about reverence. It suggests that the unknown is not a void to be filled, but a presence to be acknowledged. Beneath the Arctic glaciers, that presence is palpable. It is in the darkness that swallows light. It is in the pressure that bends steel. It is in the water that moves unseen and the life that may or may not exist. It is in the knowledge that no matter how far we go, there will always be something beyond. And perhaps that is the point. The hidden world beneath the Arctic ice is not a puzzle to be solved once and for all. It is a conversation, one that will unfold over decades, centuries and beyond. Each generation will push a little farther, learn a little more, and leave a little more mystery intact for those who come after. We will build better machines, refine our models and deepen our understanding. We will make mistakes, lose instruments, and learn from failure. And through it all, the labyrinth will continue to move. The water will continue to flow, and the darkness will continue to hold its secrets. In the end, the greatest gift the Arctic's hidden world may offer us is not its answers, but its questions. It asks us who we are when faced with the unknown. It asks us how much we are willing to risk for knowledge and how much we're willing to leave untouched. It asks us whether we can be explorers without being conquerors, whether we can learn without destroying, whether we can honor what we do not understand. These are not easy questions, but they are the questions that matter, not just beneath the ice, but everywhere we seek to explore. And so, as we look northward toward the glaciers, the darkness and the mysteries beneath them, we are reminded that exploration is not just about going farther. It is about going deeper in every sense. It is about understanding our place in a world that will always exceed our grasp. It is about accepting that some mysteries are meant to remain. The Arctic's hidden world is one of those mysteries. It resists us, humbles us, inspires us. It challenges our ingenuity and tests our resolve. It reveals pieces of itself, then slips away again, leaving us to wonder, to imagine, to dream. That dream, the dream of what lies beneath, of what might live in the darkness, of what secrets the ice still holds, is perhaps more powerful than any discovery we could make. It keeps us reaching, questioning, striving. It reminds us that there is always more to learn, always more to seek, always more beyond the horizon. And in that sense, the mystery beneath the Arctic glaciers must remain, not as a barrier, but as a beacon, not as a limit, but as an invitation, not as a failure of exploration, but as its truest expression.